Welcome to Milky Narratives. Tonight, leave behind the noise of the waking world. Relax your mind and drift with me into the quietest mysteries of the universe. 1. The light that never truly leaves. Every star you have ever admired may already be gone. Tonight, somewhere above your head, a tiny point of light is quietly crossing the darkness of space. It seems alive. It seems present. Yet there is a chance that the star creating that light died long before the first human civilization ever looked toward the heavens. If that sounds impossible, then perhaps the universe has been telling us a secret all along. What if nothing truly disappears the moment it dies? What if every ending leaves behind something that continues its journey long after the source itself has vanished? When we look into the night sky, we like to imagine that we are witnessing the universe as it exists now. We picture billions of stars burning together in this very instant, scattered across an endless ocean of darkness. But the universe has never allowed us that privilege. Instead, it shows us only memories. Everything you are about to see tonight is history, not metaphorically, literally. The moon, glowing softly above Earth, appears almost as it is. Its light takes only about 1.25 seconds to reach your eyes. The sun is different. Every sunrise you have ever watched actually happened around 8 minutes ago. If the sun somehow vanished this instant, a scenario that physics itself would forbid in such a sudden way, we would continue living beneath its warm light for another 8 minutes before darkness finally arrived. Already, reality is stranger than intuition. Now stretch your imagination farther. The brightest star in our night sky, Sirius, shines from nearly 9 light years away. The famous red giant Betelgeuse sends its ancient glow from more than 600 light years across the galaxy. Some galaxies visible through powerful amateur telescopes are so distant that the light entering your eyes tonight began traveling toward Earth before human beings had even invented agriculture. Some of the faintest galaxies photographed by the James Webb Space Telescope emitted their light more than 13 billion years ago, long before continents looked familiar, long before the Earth itself existed in its current form, long before there were oceans, trees, dinosaurs, or anyone capable of wondering what those tiny lights meant. Every direction we look into space is also a direction backward through time. The night sky is not a photograph. It is a museum whose exhibits arrive one photon at a time. Each tiny particle of light carries a message from another age, preserving an image of something that may have changed completely or may no longer exist at all. Imagine receiving a letter that has been traveling through the mail for 1,000 years. The person who wrote it has long since vanished. The house where they lived has become dust. The language itself has evolved beyond recognition. Yet the letter finally reaches your hands. The universe works in much the same way. Light never rushes. It simply keeps going. Patiently, silently, faithfully carrying the final signature of distant stars across impossible distances. This simple truth changes everything about how we understand reality. Because nothing in the universe can send information faster than light, every observation is delayed. Every telescope is a time machine. Every photograph of a distant galaxy captures an ancient chapter rather than a present moment. Astronomers never truly study the universe as it is. They study the universe as it was. The farther away something lies, the older the story becomes. Nearby stars tell recent tales. Remote galaxies whisper about cosmic childhood. The oldest light of all comes from a time when no stars had yet formed. It arrives today as the cosmic microwave background, a faint glow filling every direction in space, a quiet echo left behind from when the universe itself was only about 380,000 years old. That ancient light has traveled for almost the entire history of existence just to reach us now. Imagine how extraordinary that journey really is. Every photon has crossed expanding space without becoming lost. It has slipped past galaxies, black holes, clouds of gas, exploding stars, and drifting planets. Most never find an observer. Most continue endlessly into the darkness. But every once in a while, one lands on a telescope mirror or inside a human eye. For one brief instant, a journey billions of years long comes to an end. and in that instant, the past becomes visible. Perhaps this is why stargazing has always inspired such quiet wonder. We are not simply looking outward, we are listening to echoes. Each point of light is a survivor. Some began traveling before mammals evolved. Others departed before Earth had oxygen-rich skies. Some may have left civilizations on distant worlds, if such civilizations ever existed, long before they themselves disappeared into history. Their messages continue regardless. The universe does not erase its past. It scatters it across space. In a way, light is the greatest historian that has ever existed. It remembers without intention. It records without judgment. It carries no opinions, no emotions, no interpretations, only information, only truth frozen into motion. And unlike written history, light cannot decide to stop halfway through its journey. Once released, it belongs to the cosmos. Even if the star that created it collapses into a white dwarf, even if it explodes as a supernova, even if it disappears forever into the event horizon of a black hole, the light already on its way continues. Nothing calls it back. Nothing tells it the story has ended. This idea is strangely comforting. Perhaps endings are never as immediate as they appear. Perhaps every existence leaves traces that continue traveling through the fabric of reality long after the source itself has faded. Stars do, galaxies do. Even the atoms inside your own body still carry memories forged within stars that died billions of years before the Earth was born. The calcium in your bones, the iron flowing through your blood, the oxygen filling your lungs. Each one began inside ancient stellar furnaces that disappeared eons ago. You are, quite literally, built from things whose light may still be crossing the universe today. So the next time you look up into the quiet night, remember this. You are not merely watching stars. You are watching time itself unfold. Some of those tiny lights may already belong to worlds forever gone, yet their final greetings are still arriving, still crossing unimaginable distances, still refusing to let the universe forget that once upon a time they burned. And perhaps that is where our journey truly begins. Because if light can outlive the stars that created it, what else might survive long after the universe itself begins to change? 2. The quiet rivers between galaxies. If light can spend billions of years crossing the universe, then perhaps we should pause for a moment and ask a surprisingly simple question. What exactly is it traveling through? At first, the answer seems obvious. Space, an endless emptiness stretching in every direction. A vast stage upon which stars, planets, and galaxies quietly perform their cosmic dance. But that picture, comforting as it may be, is incomplete. Because the greatest feature of our universe is not its stars, nor its galaxies, nor even the countless planets that may circle those distant suns. The greatest feature of the cosmos is the astonishing amount of nothing in between. Imagine shrinking our Milky Way until it became the size of a single city. Every star, every nebula, every black hole, every planet would fit comfortably inside that city. Now imagine that the next city lies thousands of kilometers away, separated by empty countryside so enormous that almost nothing interrupts the journey. That begins to resemble the universe. Galaxies are not packed together like grains of sand. They are islands, brilliant, magnificent islands floating within oceans so unimaginably vast that the mind struggles to picture them. Our nearest large galactic neighbor, Andromeda, sits about 2.5 million light-years away. That number sounds impressive, but numbers often hide reality instead of revealing it. Suppose you could travel at the speed of the Voyager 1 spacecraft, the fastest human-made object ever to leave our planetary neighborhood. It would take more than 40 billion years to reach Andromeda, nearly 3 times the current age of the universe, and that is merely our closest giant neighbor. Beyond it lie millions of others, then billions, then trillions more, separated by distances so immense that even light, the fastest traveler in existence, spends millions or even billions of years quietly crossing the darkness between them. It is tempting to think of these enormous spaces as empty. After all, what else could they be? Yet modern astronomy has revealed something far stranger. These silent expanses are not truly nothing. They are threaded together by invisible structures stretching across unimaginable distances, like rivers flowing through an unseen landscape. Not rivers of water, nor rivers of gas, but rivers shaped by gravity itself. Long before galaxies existed, shortly after the universe emerged from its unimaginably hot beginning, tiny fluctuations in matter were scattered throughout space, almost perfectly smooth. Almost. Those tiny imperfections, smaller than 1 part in 100,000, would eventually change everything. Over hundreds of millions of years, gravity patiently gathered matter toward these slightly denser regions. Not quickly, gravity is wonderfully patient. It has no deadlines, no urgency. It simply pulls, little by little, century after century, million years after million years, until invisible streams of matter began connecting what would eventually become galaxies. Today, astronomers call this immense architecture the cosmic web. Its delicate filaments stretch across billions of light years, each one guiding galaxies like leaves drifting along the slowest rivers imaginable. From far enough away, the universe begins to resemble something unexpectedly familiar. Not a collection of isolated objects, but a living network. Clusters connected by slender bridges, great empty voids surrounded by glowing walls, an intricate pattern woven across the entire observable cosmos. Curiously, many scientists have noticed that this pattern resembles structures found much closer to home. Neural networks inside the human brain, fungal mycelium spreading beneath ancient forests, river systems branching across continents, even lightning splitting through storm clouds. Nature seems remarkably fond of repeating certain designs across wildly different scales. Whether this reflects something profound or simply the mathematics of complex systems remains uncertain. Yet the resemblance is difficult to ignore. The universe often appears to whisper the same geometric language again and again. But perhaps the most astonishing part of the cosmic web is that much of it remains invisible. The stars we see account for only a tiny fraction of all ordinary matter, and ordinary matter itself represents only about 5% of the total energy content of the universe. The rest is hidden from direct view. Dark matter quietly outweighs every star and planet combined. We cannot see it, we cannot touch it. No telescope has ever photographed it. Yet its gravity reveals its presence everywhere. Without it, galaxies would never have formed. Without it, these great invisible rivers would simply fall apart. Imagine standing beside a river on a moonless night. You cannot see the current, you cannot see the water itself, but floating leaves reveal the direction in which it flows. Galaxies perform much the same role. Their graceful movements reveal currents that remain forever unseen. Every slow orbit, every galactic collision, every cluster drifting toward another speaks of invisible landscapes hidden beneath reality. Perhaps that is one of the universe's most beautiful habits. Its deepest structures are rarely obvious. What appears empty often contains hidden architecture. Silence often conceals remarkable activity. Even here on Earth, emptiness is rarely empty. Between the atoms making up your body lies astonishing amounts of open space. If every atom lost that emptiness and compressed completely, the entire human race could fit inside something no larger than a sugar cube. The solid world around us is far less solid than it appears. Likewise, the empty universe is far less empty than we once imagined. Invisible particles drift through intergalactic space. Ancient photons continue journeys that began billions of years ago. Magnetic fields quietly thread enormous distances. Ghostly neutrinos pass through entire galaxies without noticing them. Even gravity itself ripples outward whenever massive objects move, sending gentle waves across space-time that continue long after their violent origins have faded. The silence between galaxies is not silent. It simply speaks a language too slow and too subtle for human senses. If we could somehow drift through one of these immense cosmic voids, the experience would challenge every instinct we possess. There would be no up, no down, no nearby landmarks, no comforting horizon. Only darkness, sprinkled with faint galaxies so distant they would resemble tiny islands floating upon a perfectly black sea. Days would lose meaning, so would directions. Even the nearest galaxy might remain millions of light years away. And yet, you would not truly be alone. Invisible rivers of gravity would still surround you, ancient light would continue passing by. Subatomic particles born inside stars would quietly cross your path. The universe would still be moving, still evolving, still carrying countless stories from places too distant to imagine. Perhaps loneliness itself is a matter of perspective. To human eyes, these enormous voids appear empty because we seek familiar things: stars, planets, life. But the cosmos is under no obligation to fill every corner with objects we recognize. Sometimes its greatest beauty lies not in what is present, but in what quietly connects everything else. Those invisible bridges stretching between galaxies remind us that separation is often an illusion. Nothing exists entirely on its own. Every galaxy belongs to a larger structure. Every cluster participates in a greater pattern. Even our Milky Way, carrying hundreds of billions of stars, is simply one small thread woven into an unimaginably larger tapestry. And perhaps we are not so different. Every thought, every breath, every heartbeat, every life, part of connections too subtle to notice in our everyday experience. The universe has always excelled at hiding its greatest masterpieces in plain sight. First, it taught us that light never truly leaves. Now it quietly reveals that even emptiness has a structure. And as our journey continues, another mystery begins to emerge from those invisible rivers. Because if gravity can weave galaxies together across billions of light years, what unseen threads might be holding the entire universe itself together? 3. The invisible threads holding everything together. Take a moment to imagine standing in complete darkness. Not the darkness of a moonless night, nor the darkness inside a deep cave, but a darkness so complete that even the nearest galaxy is millions of light years away. Around you stretches an ocean of space almost entirely empty to the eye. Yet according to everything modern astronomy has discovered, this emptiness is not truly empty. Invisible architecture surrounds you. Across unimaginable distances, galaxies are not scattered randomly like grains of sand. Instead, they appear to follow an immense, hidden pattern, as though someone stretched delicate threads across the entire universe before the first stars were even born. The remarkable part is that no telescope has ever directly photographed these threads. We know they are there because we see what gathers around them. Imagine waking up after a fresh snowfall. You cannot see the wind itself, but you immediately recognize where it has blown, because snow has drifted into long ridges and smooth curves. The invisible force reveals itself through the patterns it leaves behind. The universe behaves in much the same way. Galaxies collect where invisible rivers of gravity guide them. Clusters gather like droplets, forming along strands of spider silk. Entire superclusters seem connected by bridges stretching hundreds of millions of light years across space. Astronomers call this breathtaking arrangement the cosmic web. It may be the largest known structure in existence. If you could somehow zoom far enough away from the observable universe, the countless galaxies might no longer resemble isolated islands of light. Instead, they would look surprisingly similar to neurons inside a human brain, or tiny veins inside a living leaf. Bright intersections connected by impossibly long filaments. Between those filaments lie enormous voids, regions so empty that a traveler could drift for tens of millions of light years without passing another large galaxy. The universe, viewed from this impossible distance, almost appears alive. Of course, appearances can be misleading. The resemblance between neural networks and the cosmic web is likely coincidence rather than evidence of some deeper biological connection. Yet it reminds us that nature often favors similar patterns across astonishingly different scales. The same mathematics that shapes bubbles in foam can also describe clusters of galaxies. The same principles that organize rivers across continents can sometimes describe plasma flowing through interstellar space. Patterns repeat because physics repeats, and nowhere is that repetition more majestic than within the cosmic web. But what are these invisible threads actually made of? That question leads us into one of science's greatest mysteries. When astronomers carefully measured how galaxies rotate, something unexpected appeared. Stars near the outer edges of galaxies were moving far too quickly. According to everything visible, the stars, the gas, the dust, those galaxies should have flown apart long ago. Instead, they remained stable. Something unseen was providing additional gravity, something with mass, something that neither emitted nor reflected light. This mysterious substance became known as dark matter. Despite decades of research, no one has directly detected a dark matter particle in a laboratory. We infer its existence through its gravitational influence. Like footprints across fresh snow, dark matter leaves evidence without revealing its face. Current observations suggest that ordinary matter, the atoms making up stars, planets, oceans, trees, and ourselves, accounts for only about 5% of the universe's total contents. Dark matter contributes roughly 27%. The remaining majority appears to consist of an even stranger phenomenon known as dark energy, responsible for the accelerated expansion of the universe. In other words, everything humanity has ever touched belongs to the smallest visible fraction of reality. It is a humbling thought. Every mountain, every ocean, every city, every civilization, every person who has ever lived. Together, they make up only a tiny layer floating atop a far deeper cosmic mystery. Without dark matter, galaxies might never have formed at all. Soon after the Big Bang, tiny variations in density existed throughout the hot young universe. Gravity slowly amplified those slight differences. Dark matter, unaffected by light and radiation, began gathering first. It formed enormous gravitational scaffolds long before stars ignited. Ordinary matter later drifted toward these invisible frameworks, cooling into clouds that eventually collapsed into galaxies. One might think of dark matter as the hidden framework beneath a vast cathedral. Visitors admire stained glass windows, towering arches, and carved stone. Yet without the unseen foundation beneath the ground, none of the visible beauty could stand. The stars are the cathedral we notice. Dark matter may be the foundation quietly supporting it all. Computer simulations offer an extraordinary glimpse into this process. Starting with conditions measured from the early universe, scientists allow gravity to shape billions of virtual particles across cosmic time. The result is astonishing. Filaments emerge naturally. Clusters grow where threads intersect. Immense voids expand between them. When these simulations are compared with maps of real galaxies, the resemblance is almost uncanny. The universe seems to have woven itself according to simple laws repeated across billions of years. Perhaps simplicity is one of nature's greatest strengths. From only gravity, time, and tiny fluctuations, unimaginable complexity slowly unfolds. It is rather like frost spreading across a winter window. The intricate patterns appear almost artistic, yet each delicate branch follows straightforward physical principles. No artist directs every crystal. Order arises naturally. The cosmic web may represent the largest example of this quiet self-organization. Yet even these colossal structures are not permanent. As billions of years pass, gravity continues pulling nearby galaxies together. Clusters become denser, some galaxies merge, others are flung away through gravitational encounters. Meanwhile, dark energy gently stretches the fabric of space itself. On the largest scales, distant regions drift farther apart. Eventually, enormous portions of today's observable universe will recede beyond our cosmic horizon. Future civilizations, if any exist trillions of years from now, may see only their local group of galaxies. The rest of the cosmic web will have faded beyond visibility forever. Its invisible threads will remain, but their distant lights will no longer reach anyone capable of observing them. There is something strangely poetic about this. The greatest structure we know may slowly disappear, not because it ceases to exist, but because space itself quietly carries its distant parts beyond every possible horizon. Knowledge, too, has horizons. Human understanding continues expanding, yet every answer seems to uncover new questions waiting beyond. What exactly is dark matter? Why does dark energy exist? Did the cosmic web emerge exactly as current theories predict, or are deeper laws still hidden beneath our equations? No one yet knows. Perhaps that uncertainty is part of what makes astronomy so captivating. Unlike many mysteries in fiction, these questions are real. Somewhere above us tonight, invisible rivers continue guiding galaxies exactly as they have for nearly 14 billion years. Whether anyone watches them or not, gravity patiently shapes the universe, slowly, silently, without hurry. And perhaps there is comfort in that. Our own lives often feel filled with deadlines, constant movement, and endless noise. Yet the cosmos reminds us that the grandest transformations require extraordinary patience. Galaxies take hundreds of millions of years to dance around one another. Clusters assemble over billions of years. Invisible threads stretch across distances so vast that light itself spends ages traveling from one end to the other. Against that backdrop, our hurried moments become wonderfully small. Not insignificant, simply part of a much larger story. Maybe every life resembles a single glowing galaxy suspended within an unseen network of countless connections. Many of those connections remain invisible until viewed from far enough away, just as the cosmic web reveals itself only across unimaginable distances. Perhaps meaning in our own lives sometimes appears only with the passage of time. The universe may be woven together by threads we cannot see, and perhaps in quiet ways, so are we. 4. Where time begins to slow. Imagine placing two perfectly synchronized clocks side by side. They begin their journey ticking together, each second arriving in flawless harmony. One clock remains safely on Earth, resting quietly on a table. The other is carried aboard a spacecraft that ventures toward one of the most extreme places in the universe, a region where gravity becomes so overwhelming that space itself seems to bend under its own weight. Years later, the spacecraft returns. The travelers step outside, hardly feeling that much time has passed. But when they compare their clocks, something astonishing has happened. The clock that stayed behind has counted far more seconds. The travelers have quite literally experienced less time. This is not science fiction. It is one of the strangest and most beautiful predictions ever made about reality, and every experiment performed over the past century continues to confirm it. Time is not the steady river we once imagined. It can stretch, it can slow. It can even flow at different speeds depending on where you are. For most of human history, time felt absolute. Morning always followed night. The seasons repeated. A heartbeat lasted as long as a heartbeat. Whether someone stood atop a mountain or beside the sea, time seemed identical for everyone. It was comforting to believe the universe carried one enormous invisible clock, quietly ticking for all existence alike. Then, in the early 20th century, Albert Einstein proposed something almost impossible to accept. Time, he argued, is woven together with space. They are not separate things. Instead, they form a single fabric: space-time. Imagine stretching a giant rubber sheet. Place a marble upon it, and the sheet remains nearly flat. Now place a heavy bowling ball in the center. The surface bends. Nearby marbles begin rolling toward the depression, not because an invisible hand pulls them, but because the surface beneath them has changed shape. Gravity, according to Einstein, works in much the same way. Mass tells spacetime how to curve. Curved spacetime tells matter how to move. But something else happens as this cosmic fabric bends. Time itself begins to change. Near massive objects, time slows. Far away, it flows more quickly. The stronger the gravity, the more dramatic the difference becomes. On Earth, this effect is incredibly tiny. Every one of us experiences slightly different time depending on our position. Your feet, being closer to Earth's center, actually age just a fraction more slowly than your head. The difference is unimaginably small, far too tiny to notice in everyday life. But modern atomic clocks can measure it with astonishing precision. If two identical clocks are placed only a few centimeters apart in height, today's instruments can detect the difference. Reality is stranger than our senses reveal. Even satellites orbiting high above Earth must account for this phenomenon. The satellites that make GPS navigation possible experience weaker gravity than people standing on the surface. As a result, their clocks run slightly faster. Without correcting for Einstein's equations every single day, GPS systems would accumulate errors of several kilometers in remarkably little time. Every journey guided by your phone quietly depends upon the fact that time itself does not flow equally everywhere. We often think of relativity as an exotic theory reserved for distant galaxies. In truth, it quietly helps us find the nearest cafe. Yet Earth's gravity is gentle compared with the monsters scattered across the cosmos. Imagine approaching a neutron star. These extraordinary objects contain more mass than our sun, compressed into a sphere barely 20 kilometers across. A single teaspoon of neutron star material would weigh billions of tons on Earth. Gravity near such an object becomes almost beyond imagination. If you could somehow survive hovering nearby, time for you would noticeably slow compared with someone watching safely from far away. Hours might pass for you, while much more time unfolds elsewhere. Closer still lie black holes, the most extreme gravitational environments known. A black hole is not merely an object. It is a place where space-time curves so dramatically that every path leads inward. Its gravity becomes so overwhelming that not even light can escape once it crosses a boundary known as the event horizon. From a safe distance, something extraordinary appears to happen. Imagine watching an astronaut slowly descend toward the event horizon of a black hole. At first, everything seems normal. The astronaut waves, signals continue arriving. But as they fall deeper into the black hole's gravity, their clock appears to slow. Their movements become more gradual. The light reaching you loses energy, shifting toward redder wavelengths. Eventually, the astronaut seems almost frozen in place. You never actually witness them crossing the event horizon. Instead, they fade, dimmer, redder, slower, until they quietly disappear into darkness. To the distant observer, time near the event horizon appears to nearly stop. Yet from the astronaut's own perspective, something entirely different occurs. Their clock continues ticking normally. Their heartbeat remains steady. Their thoughts proceed naturally. They do not suddenly feel frozen. To them, it is the outside universe that begins behaving strangely. As they approach the event horizon, distant clocks seem to accelerate. Stars evolve more rapidly. Galaxies race through ages. If they could somehow look outward safely, they might watch thousands or even millions of years unfold beyond them, while only hours pass according to their own experience. Time has not stopped. It has simply become different for different observers. This idea challenges one of our deepest intuitions. We instinctively believe there exists a universal now. Surely there must be one moment shared by everyone in existence. Relativity gently tells us otherwise. The universe possesses no single master clock. Each observer carries their own measure of time. Every path through space becomes its own path through time. In a sense, every living creature writes a unique rhythm into the fabric of the cosmos. That realization can feel unsettling, yet it is also strangely comforting. It reminds us that reality is richer than appearances suggest. The universe is not obligated to match human intuition. It is far more imaginative than our ancestors ever dreamed. Even science fiction often struggles to match the elegance of actual physics. Hollywood frequently imagines time travel as a machine carrying someone into the past. Reality offers something subtler. Nature already allows travel into the future, not by jumping instantly across centuries, but by changing the rate at which time flows. Astronauts aboard the International Space Station experience this every day. Moving at nearly 28,000 kilometers per hour while orbiting Earth, they age just a tiny fraction differently from people on the ground. The effect is microscopic, yet entirely real. Every astronaut who has returned home has technically traveled a little farther into Earth's future than the rest of us. It may amount to only milliseconds, but it happened. Time travel, in its gentlest form, already exists. Perhaps nowhere has this concept captured the public imagination more vividly than in stories about black holes. In the film Interstellar, explorers visit a planet orbiting dangerously close to a supermassive black hole. There, 1 hour corresponds to roughly 7 years for people waiting far away. Although the exact scenario was dramatized for storytelling, it was inspired by genuine relativistic physics. Gravity truly can create astonishing differences in the passage of time. The universe itself writes narratives more extraordinary than fiction. As we continue exploring deeper into space, relativity becomes increasingly important. The earliest galaxies formed when the universe itself was young. The light arriving at our telescopes tonight began its journey billions of years ago. Looking farther into space literally means looking farther back in time. Every observatory is therefore not just a window into distant places. It is a window into history. The James Webb Space Telescope does not simply photograph remote galaxies. It photographs ancient moments. Each image is a message carried across billions of years, patiently waiting for intelligent eyes to receive it. The night sky is not a collection of objects existing simultaneously. It is a mosaic assembled from countless different moments in cosmic history. Some stars we admire may already have changed. Some galaxies have evolved beyond recognition. Some worlds may no longer exist. Yet their light continues traveling faithfully through the darkness, preserving moments long after they have passed. Perhaps that is one of the most beautiful lessons relativity offers. Time is not an enemy rushing us toward an ending. It is part of the universe's grand design, flowing differently through every corner of existence. Each second we experience is uniquely ours, woven into an endless cosmic tapestry stretching across billions of years. Somewhere tonight, beneath unfamiliar constellations, another observer may be measuring time differently from us, not because their clock is broken, but because the universe itself has chosen a different rhythm. And as our journey continues, we will soon encounter objects so extreme that even light, the fastest traveler in existence, can no longer escape their grasp. There, the relationship between space, gravity, and time becomes even more mysterious, inviting us one step closer to understanding the deepest secrets hidden within the cosmos. 5. The silent lives of wandering planets. Some planets may spend eternity drifting through darkness without ever orbiting a single star. When we imagine a planet, we almost always picture it circling a warm, brilliant sun. The rhythm feels natural. A star rises each morning, sets each evening, and bathes its worlds in light for billions of years. Every familiar planet in our own solar system follows this quiet celestial dance. Mercury races close to the Sun. Earth circles comfortably within the habitable zone. Neptune glides patiently through the distant darkness, yet even it never loses sight of the star that gave birth to it. For generations, astronomers assumed this was simply how planets existed. A planet belonged to a star. Without one, it seemed almost impossible to imagine a world surviving at all. Yet the universe once again proved to be far stranger than our expectations. Somewhere beyond the countless constellations visible tonight, entire planets wander alone. No sunrise, no sunset, no parent star, no familiar seasons, only endless darkness stretching in every direction. These are known as rogue planets, sometimes called wandering planets, worlds that have escaped the gravitational embrace of every star. If our own Earth suddenly became one of them, the transformation would be unimaginably swift. Within days, the blue skies would darken. The warmth that has nurtured life for over 4 billion years would begin fading away. Plants would no longer receive sunlight for photosynthesis. Surface temperatures would plummet. The oceans would slowly freeze from the top downward, forming layers of ice that could eventually grow kilometers thick. Cities would disappear beneath snow and frost. Clouds would vanish as the atmosphere cooled. The familiar blue marble would slowly transform into a silent sphere wrapped in eternal night. It is a chilling image, yet for some planets, this lonely existence may not be an accident. It may simply be the way they have always lived. How does an entire planet become lost? One possibility begins during the violent birth of planetary systems. Young stars are chaotic places. New planets form inside enormous disks of gas and dust, each pulling gently on its neighbors. As more worlds emerge, gravity becomes increasingly complicated. Large planets may drift inward, others move outward. Some experience close encounters that resemble a cosmic game of billiards. Imagine several massive planets passing near one another over millions of years. Each encounter slightly alters their paths. Eventually, one unlucky world receives just enough of a gravitational push to exceed the escape velocity of its entire solar system. It does not explode. It does not collide. It simply keeps moving. Farther, farther still, until the star that once illuminated its skies becomes another distant point of light among billions. Gravity never calls it back. The planet begins a journey with no destination. An endless voyage through interstellar space. Our own solar system may have experienced similar episodes long before Earth existed. Computer simulations suggest that the early solar system was far less orderly than it appears today. The giant planets likely migrated across enormous distances, reshaping the architecture of the system. Some smaller worlds may have been scattered outward forever, becoming silent travelers between the stars. If so, our sun may have lost children we will never know. Yet not every rogue planet is necessarily an exile. Some may have formed independently. Inside giant molecular clouds, regions dense enough to create stars sometimes fail to gather sufficient mass. Instead of igniting nuclear fusion, they simply collapse into enormous planetary objects. They are born alone. No sunrise ever greets them. No star ever claims them. From the very beginning, darkness is simply home. This possibility challenges one of our deepest assumptions about planetary formation. Perhaps stars are not always required. Perhaps the universe has more than one way of creating worlds. For astronomers, discovering rogue planets is extraordinarily difficult. Normally, planets reveal themselves because they orbit bright stars. We detect tiny dips in starlight as planets pass in front, or we measure the slight wobble of a star being tugged by an unseen companion. But a rogue planet has neither advantage. It shines with almost no light of its own. It orbits nothing. Against the vast blackness of space, it becomes nearly invisible. Finding one is like searching for a grain of charcoal drifting across a moonless night. Fortunately, gravity leaves subtle fingerprints. Occasionally, a wandering planet drifts directly between Earth and a distant background star. Its gravity bends the star's light ever so slightly, briefly magnifying it before continuing onward. This phenomenon, called gravitational microlensing, lasts only a short time. Then the rogue planet disappears once more into darkness. From these fleeting events, astronomers have uncovered evidence that our galaxy may contain astonishing numbers of wandering worlds. Some estimates even suggest rogue planets could rival, or perhaps exceed, the number of stars in the Milky Way. Imagine that for a moment. Our galaxy contains hundreds of billions of stars. Now imagine at least that many lonely planets drifting silently between them. Invisible oceans of worlds crossing the darkness. Entire landscapes no telescope has ever photographed. Mountains no sunrise has ever illuminated. Frozen valleys untouched for billions of years. It is a humbling thought. Even more surprising is the possibility that some rogue planets may not be entirely frozen. At first, this seems impossible. Without sunlight, how could any warmth survive? The answer lies deep beneath the surface. Large planets retain internal heat generated during their formation. Radioactive elements within their rocky interiors continue releasing energy through slow decay. On Earth, this geothermal warmth powers volcanoes, hot springs, and deep hydrothermal vents. Even today, much of our planet's interior remains astonishingly hot. If a rogue planet possesses enough mass and a sufficiently thick atmosphere, this internal heat could become trapped beneath insulating layers. Although the surface might remain unimaginably cold, liquid water could persist far below the ice. An underground ocean hidden beneath kilometers of frozen crust, quietly enduring through cosmic ages. Remarkably, we already know places somewhat similar. Several moons in our own solar system, including Europa and Enceladus, harbor global oceans beneath icy shells despite receiving relatively little sunlight. Their warmth comes primarily from gravitational interactions rather than solar heating. Life, at least in principle, may not require direct sunlight after all. Deep within Earth's oceans, entire ecosystems flourish around hydrothermal vents. There, bacteria draw energy from chemical reactions instead of sunlight. Strange creatures, tube worms, giant clams, and ghostly shrimp depend upon these invisible energy sources. They remind us that biology can be astonishingly adaptable. If such environments exist beneath the frozen crusts of rogue planets, could simple life survive there as well? No one knows. The idea remains speculative. Yet each new discovery expands the boundaries of what we consider possible. The universe repeatedly teaches us humility. Every time we believe we understand the conditions required for life, nature quietly presents another exception. Perhaps somewhere in the darkness, beneath endless layers of ancient ice, microscopic organisms continue living in complete isolation. No sunrise has ever touched them. No star has ever warmed their skies. Yet they persist, unaware of the unimaginable emptiness surrounding their hidden ocean. It is a strangely peaceful image, a tiny oasis drifting endlessly through an ocean of stars. For any hypothetical inhabitants, if they existed, the concept of a sun might never even arise. Their entire universe would consist of warm water, rocky caverns, mineral-rich currents, and a ceiling of ice stretching forever overhead. The stars themselves would remain unknown. Sometimes we assume our perspective is universal, but every environment writes its own understanding of reality. Even loneliness takes on a different meaning in the cosmos. From our perspective, a rogue planet seems isolated beyond measure. Yet space itself is so vast that even planets orbiting stars remain separated by incomprehensible distances. Whether bound to a sun or wandering freely, every world experiences a profound solitude. Perhaps what changes is not isolation itself, but the source of light that accompanies it. There is also a poetic beauty in these wandering worlds. They are reminders that not every journey follows a predetermined path. Some objects spend billions of years without belonging to any system. They drift patiently through the galaxy, carrying frozen mountains, silent plains, buried oceans, and memories of ancient origins that no observer may ever uncover. Long after civilizations rise and disappear, long after familiar constellations rearrange themselves through the slow motions of stars, these solitary planets will continue their quiet voyage, crossing invisible rivers between galaxies, passing beneath ancient nebulae, watching nothing, waiting for nothing, simply existing. And perhaps that is enough, because in the universe, even the loneliest travelers still remain part of something unimaginably vast, a cosmic story in which every world, whether illuminated or forgotten, contributes another quiet chapter to the endless journey through space and time. 6. Oceans hidden beneath endless ice. Before we continue our journey through the cosmos, let us imagine a world where the sun never rises. No dawn paints the horizon with gold. No blue sky stretches overhead. No warm afternoon breeze carries the scent of forests or oceans. Instead, an endless ceiling of ice covers everything, reaching farther than the eye could ever see. Beneath it lies a vast, silent ocean that has remained hidden for billions of years. At first glance, such a place seems utterly lifeless. After all, nearly every form of life we know depends directly or indirectly on sunlight. Plants convert light into energy. Animals eat plants or other animals. Entire ecosystems are ultimately powered by a star. It feels almost impossible to imagine life without sunshine. And yet, the universe may have quietly prepared countless exceptions. Perhaps warmth is not the true requirement for life. Perhaps light is not the essential ingredient we once believed. Perhaps all life truly needs is liquid water, a source of energy, and enough time. If that is true, then some of the most promising places to search for life may not be warm planets at all. They may be frozen worlds. For centuries, ice represented death in our imagination. Frozen landscapes appeared empty, silent, and inactive. Early astronomers looked at icy moons through their telescopes and assumed they were little more than frozen rocks drifting endlessly around distant planets. They seemed beautiful, certainly, but alive? Almost no one imagined such a possibility. Everything changed as spacecraft began visiting the outer solar system. As our robotic explorers approached these frozen moons, they revealed landscapes unlike anything humanity had ever seen. Instead of dead worlds, scientists discovered evidence of hidden activity. Cracked surfaces, moving ice, mysterious fractures stretching hundreds of kilometers, and perhaps most astonishing of all, oceans. Entire global oceans concealed beneath immense shells of frozen ice. One of the first worlds to completely reshape our understanding was Europa, one of Jupiter's largest moons. From a distance, Europa appears smooth and brilliant, its icy shell reflecting sunlight like polished marble. But close inspection tells another story. Its surface is crisscrossed by dark lines resembling enormous fractures. Very few impact craters remain visible. That is unusual. Old worlds accumulate countless craters over billions of years. Europa appears strangely young. Something keeps renewing its surface. Scientists believe the explanation lies beneath the ice. Hidden below may be a global ocean containing more liquid water than all of Earth's oceans combined. Imagine that. A moon smaller than Earth's own moon could possess twice as much water as our entire planet, yet almost none of it has ever seen sunlight. The ice above may be 15 to 25 kilometers thick. Below it, the ocean could extend another 100 kilometers downward. An unimaginable volume of dark, liquid water quietly circling Jupiter. The next surprise came from an even smaller moon. Enceladus, orbiting Saturn, measures only about 500 kilometers across. By comparison, Earth's moon is nearly 7 times larger. Few expected such a tiny world to remain active. Then, in 2005, NASA's Cassini spacecraft witnessed something extraordinary. Towering geysers erupted from fractures near Enceladus's south pole. Enormous jets of water vapor, ice particles, and organic molecules blasted hundreds of kilometers into space. The tiny moon was literally spraying pieces of its hidden ocean into the vacuum. Cassini flew directly through these plumes. Its instruments detected water, salts, methane, carbon dioxide, and complex organic compounds, the very kinds of ingredients scientists associate with environments capable of supporting life. No one claimed life had been found, but for the first time, humanity sampled material from an alien ocean without drilling through kilometers of ice. The universe had opened a tiny window into one of its hidden seas. But this raises a fascinating question. If sunlight cannot penetrate these oceans, where does their energy come from? The answer lies deep inside the worlds themselves. Gravity. As Europa circles Jupiter and Enceladus orbits Saturn, the enormous gravitational pull of these giant planets constantly stretches and squeezes their interiors. This process is known as tidal heating. Imagine repeatedly bending a metal wire. Eventually, it becomes warm. Now imagine entire moons being gently flexed by gravity for billions of years. The continuous deformation generates heat deep beneath their icy crusts. That warmth prevents the hidden oceans from freezing solid. It also powers geological activity, driving currents, fractures, and perhaps even underwater volcanic systems. On Earth, similar environments exist at the bottom of our oceans. Far below where sunlight can reach, hydrothermal vents continuously release superheated, mineral-rich water into the darkness. Around these vents flourish entire ecosystems, giant tube worms, blind shrimp, strange bacteria, creatures that never depend upon sunlight. Instead, microscopic organisms extract energy directly from chemical reactions involving sulfur, methane, and minerals released from Earth's interior. This process, known as chemosynthesis, demonstrates that sunlight is not the only path toward sustaining life. Nature has already shown us another possibility. If hydrothermal vents exist on Europa or Enceladus, and many scientists believe they might, then similar chemical energy sources could potentially support microbial ecosystems beneath the ice. Imagine tiny organisms slowly drifting through warm underwater currents beneath kilometers of frozen crust. No sunrise has ever illuminated their world. No stars sparkle overhead. No seasons ever change. Their universe consists only of warm water, mineral-rich vents, gentle currents, and endless darkness. Would such creatures ever wonder whether another world exists beyond the ice? Would they imagine the stars? Or would the ocean itself seem infinite? It is remarkable how often our assumptions are challenged by reality. For thousands of years, humanity believed life required Earth-like conditions. Then we discovered organisms living inside boiling acidic springs, microbes surviving beneath Antarctic glaciers, bacteria thriving kilometers beneath Earth's crust, tiny animals enduring the vacuum of space for brief periods. Every discovery reminds us that life is astonishingly resilient. Perhaps the universe has been quietly experimenting with biology in places we once dismissed entirely. Frozen moons are no longer viewed as barren wastelands. They have become some of the most exciting destinations in planetary science. Future missions hope to investigate them more closely. NASA's Europa Clipper spacecraft is designed to perform repeated flybys of Europa, studying its ice shell, internal ocean, chemistry, and potential habitability in unprecedented detail. Meanwhile, the European Space Agency's JUICE mission is exploring Jupiter's icy moons from another perspective, helping scientists understand these hidden worlds as interconnected members of a remarkable planetary system. Although neither spacecraft is designed to search directly for living organisms, both will provide crucial clues about whether these oceans possess the ingredients necessary for biology. One day, future explorers may attempt something even more ambitious. Imagine a robotic probe landing gently upon Europa's frozen surface. It begins melting downward, slowly descending kilometer after kilometer through ancient ice. Weeks become months, months become years. Finally, after an unimaginably long journey, the probe breaks through into liquid water that has remained isolated since before multicellular life evolved on Earth. Its lights illuminate an ocean no human eye has ever seen. Tiny particles drift silently through the water. Minerals rise from distant hydrothermal vents. Perhaps nothing else appears, or perhaps something moves. Even the faintest sign of biology would transform humanity forever. We would no longer ask whether life exists beyond Earth. We would know that the universe can create life more than once. And if it happened twice within our own solar system, how many times might it have happened across the Milky Way? The implications become almost impossible to comprehend. There are hundreds of known icy moons orbiting the giant planets in our solar system. Beyond them lie countless rogue planets wandering between the stars, some of which may hide buried oceans warmed by radioactive decay. Then come the billions upon billions of exoplanets scattered throughout our galaxy. Many may possess icy shells protecting vast underground seas. Perhaps oceans hidden beneath ice are not rare exceptions. Perhaps they are among the most common habitats in the universe. If so, the cosmos may be far quieter than we imagined. Not empty, but filled with unseen oceans gently flowing beneath frozen crusts. Worlds where darkness has lasted for billions of years. Worlds that have never known a sunrise. Worlds where life, if it exists, has evolved in complete isolation from the stars. There is something deeply peaceful about that possibility. We often associate darkness with emptiness. Yet beneath the coldest surfaces, warmth may patiently endure. Hidden beneath silence, gentle currents may still flow. Even in places where light has never reached, existence may quietly continue. Perhaps that is one of the universe's most comforting lessons. Hope does not always shine brightly. Sometimes it waits beneath layers of ancient ice, unseen but persistent, carrying the possibility that life can flourish in the most unexpected corners of creation. And as our voyage carries us farther into the deep universe, we will soon encounter an even greater mystery, one that stretches across entire galaxies. Invisible structures may be shaping everything we see, even though no telescope has ever observed them directly. 7. The strange chemistry that could replace life as we know it. Perhaps somewhere in the universe, life was never built from the same ingredients as ours. Every living thing you have ever known shares the same remarkable chemical foundation. The trees that sway gently in the wind, the whales swimming through Earth's deepest oceans, the birds crossing the morning sky, even the tiny bacteria hidden beneath ancient rocks. Despite their extraordinary diversity, they all speak the same molecular language. Their cells are built primarily from carbon. Their chemistry depends upon liquid water. Their genetic instructions are written using DNA or RNA. Every heartbeat, every leaf, every thought, every breath is part of a single family tree that began billions of years ago on one small planet. Because Earth is the only example of life we have ever observed, it is only natural that we search for similar worlds elsewhere. We look for planets with liquid water, comfortable temperatures, rocky surfaces, atmospheres not too thick and not too thin. In many ways, we search for another Earth. But what if that approach is too narrow? What if life is far more imaginative than we are? Perhaps somewhere among the hundreds of billions of stars in our galaxy, biology discovered an entirely different recipe, one that does not resemble our own, one that would seem almost alien in every possible way. It is an unsettling thought. If such life existed, would we even recognize it? Or might we overlook an entire living ecosystem simply because it does not fit our expectations? Science has repeatedly taught us that nature enjoys surprising us. For centuries, people believed all swans were white. Then black swans were discovered. It did not change the definition of a swan. It changed our understanding of possibility. Perhaps Earth is the white swan of biology. Beautiful, common to us, yet not the only form life can take. Among all the elements in the periodic table, carbon occupies a very special place. Its atoms can bond with 4 other atoms simultaneously, allowing it to create astonishingly complex molecules, long chains, branching networks, elegant rings. tiny molecular machines. Proteins, sugars, fats, DNA all depend upon carbon's remarkable flexibility. No other known element rivals its ability to build such intricate structures. For this reason, carbon is often described as the backbone of life. Yet it is not entirely alone. Just beneath carbon on the periodic table sits silicon. Like carbon, silicon can form 4 chemical bonds. This similarity has fascinated scientists and science fiction writers for decades. Could silicon replace carbon? Could an entirely different form of life emerge? At first glance, the idea seems promising. Silicon is abundant. Earth itself contains enormous amounts of it within rocks and minerals. Many planets possess silicon-rich crusts. Why not build living organisms from it? The answer lies in chemistry. While silicon resembles carbon in certain ways, it behaves very differently under ordinary conditions. Carbon forms stable, flexible molecules capable of extraordinary complexity. Silicon compounds are generally less versatile. Many become rigid solids, others react too easily. Still others fail to support the intricate chemistry required for rapidly changing biological systems. Perhaps most importantly, carbon dioxide exists as a gas that organisms can easily exchange with the atmosphere. Silicon's equivalent, silicon dioxide, is quartz. Imagine trying to breathe tiny crystals instead of invisible gas. Life becomes considerably more complicated. For these reasons, most chemists believe carbon remains vastly superior for supporting biology as we know it. But notice those final words, as we know it. The universe may not be limited to environments like Earth's. Suppose an alien world possesses temperatures of several hundred degrees Celsius, or pressures thousands of times greater than our atmosphere. Perhaps there, silicon chemistry behaves in ways unfamiliar to us. Nature often reveals surprising behaviors under extreme conditions. After all, water itself behaves very differently near absolute zero or inside the crushing interiors of giant planets. Chemistry changes with environment. Perhaps biology does too. Even if silicon proves unlikely, countless other possibilities remain. Consider water. Every living cell on Earth depends upon it. Water dissolves nutrients, carries waste, regulates temperature, supports countless chemical reactions. Its properties are almost miraculous. Liquid across a wide temperature range, expanding when frozen, excellent at transporting heat. It seems almost perfectly designed for life. Yet water may not be the only useful liquid. On Saturn's largest moon, Titan, lakes and rivers flow across the landscape. At first, this sounds wonderfully familiar until we discover what fills them. Not water. Methane, ethane, liquid hydrocarbons. Titan is so cold, around -179 degrees Celsius, that water behaves like solid rock. Instead, methane performs many of the roles water fills on Earth. Clouds form, rain falls, rivers carve valleys, lakes collect across enormous plains. Entire weather systems unfold beneath a thick orange atmosphere. It is the only world besides Earth known to possess stable liquids on its surface. Imagine standing upon Titan. The sunlight would appear hundreds of times dimmer than on Earth. A thick golden haze would soften the landscape. Dark rivers would slowly wind across frozen plains made of water ice harder than granite. Above you, methane clouds drift quietly through the orange sky. If life evolved here, it might not dissolve in water at all. Its chemistry could depend upon liquid methane. Its cells, if they could even be called cells, might function at temperatures where earthly biology freezes completely. Scientists have proposed fascinating theoretical structures known as azotosomes, hypothetical cell-like membranes made not from familiar fats, but from nitrogen-containing molecules, capable of remaining flexible in Titan's liquid methane. No one knows whether such structures actually exist. They remain speculative, yet they demonstrate an important point. Once we stop assuming Earth must be the universal template, entirely new possibilities begin to emerge. The search for life becomes less about finding copies of ourselves and more about discovering nature's creativity. There are even more exotic ideas. Some researchers have wondered whether plasma, the electrically charged gas found inside stars, could organize into self-sustaining patterns. Others speculate about life inside the dense atmospheres of gas giants, where floating microorganisms might drift endlessly upon rising currents. Still, others ask whether entirely unfamiliar forms of chemistry could emerge under the immense pressures inside icy super-Earths or beneath the clouds of distant exoplanets. Most of these ideas remain highly speculative. There is currently no evidence that such life exists, but speculation, when guided by physics and chemistry, serves an important purpose. It reminds us not to confuse the limits of our imagination with the limits of reality. History offers a gentle warning. Not long ago, many scientists believed planets outside our solar system might be rare. Today, we know of thousands. People once assumed galaxies beyond the Milky Way did not exist. Then telescopes revealed billions. Again and again, the universe has expanded our expectations. Perhaps biology will someday do the same. The deeper lesson reaches beyond chemistry itself. When we search for life elsewhere, we are also asking a profound philosophical question. Are we searching for ourselves? Or are we searching for something entirely different? If an alien organism shared our DNA, breathed oxygen, and looked vaguely familiar, we might feel reassured. But what if true extraterrestrial life is so fundamentally different that communication becomes almost impossible? Would we still recognize it as life? Suppose a probe lands upon an alien world. Its instruments search for oxygen, chlorophyll, amino acids, and DNA. Finding none, it reports a barren landscape. Yet beneath the surface, an entirely different chemistry quietly flourishes, one our detectors were never designed to notice. The greatest danger in exploration is not failing to look. It is looking only for what we already expect to find. That realization has changed modern astrobiology. Scientists now design missions that search not merely for Earth-like biology, but for broader signs of chemical imbalance, complex organization, and unexpected molecular patterns. Rather than asking, is there life exactly like ours, they increasingly ask, could something here be behaving like life? The distinction is subtle, yet it may determine whether humanity recognizes its first encounter with alien biology. There is something wonderfully humbling in this perspective. Life on Earth has spent nearly 4 billion years exploring one path through chemistry. A magnificent path, a successful path, but perhaps not the only one. Somewhere beyond the distant stars, another world may have followed a different route entirely. Different molecules, different solvents, different temperatures, different evolution, yet driven by the same quiet tendency toward complexity, adaptation, and persistence. The universe may not simply repeat the same story over and over. It may write countless versions of it, each using a different alphabet. And if that is true, then every new telescope, every robotic spacecraft, and every future mission becomes more than a search for neighbors. It becomes an exploration of possibility itself, because perhaps the greatest discovery awaiting humanity is not another Earth. It is the realization that life, in all its quiet determination, is far more inventive than we ever dared imagine. If these quiet explorations help you relax before sleep, don't forget to subscribe and join us for future journeys among the stars. Our voyage is only just beginning, and ahead of us lies another mystery, one that asks not what life is made of, but how entire galaxies remember events that happened billions of years ago, carried forever by light itself. 8. When gravity becomes memory. There is something strangely comforting about the idea that the universe remembers. Not through words, not through photographs, not through records written in light, but through gravity itself. Every star that has ever existed, every galaxy that has ever collided, every black hole that has ever formed, has left behind tiny distortions in the fabric of space and time. Long after the brilliant flashes of light have faded into darkness, these distortions continue traveling silently across the cosmos. In a way, gravity becomes memory. Unlike light, which can be blocked, scattered, or absorbed, gravitational waves move through almost everything. They pass effortlessly through clouds of gas, entire galaxies, even planets, barely noticing that anything lies in their path. For billions of years, they simply continue. Imagine dropping a pebble into a perfectly still lake. The ripples spread outward in every direction. Even after the pebble disappears beneath the surface, the waves continue moving long after the event itself is over. The universe behaves in a surprisingly similar way. When enormous objects accelerate, especially when two black holes spiral toward one another, they send ripples through space itself. not waves traveling through space, waves made of space. This remarkable prediction came from Albert Einstein over 100 years ago as part of his theory of general relativity. At the time, even Einstein doubted that anyone would ever detect such unimaginably tiny distortions. The waves would simply be too small, far too small. By the time they reached Earth, they would stretch and compress distances by less than the width of a single atomic nucleus over several kilometers. It seemed impossible. Yet nature often hides its greatest stories inside the faintest whispers. In 2015, scientists operating the Laser Interferometer Gravitational Wave Observatory, better known as LIGO, detected these ripples for the first time. The signal lasted only a fraction of a second. It came from two black holes that had collided around 1.3 billion years ago. When dinosaurs still ruled Earth, those black holes had already completed their violent dance. The collision itself released more energy in an instant than all the stars in the observable universe combined emit as light during that same brief moment. And yet, by the time the waves reached us, they were astonishingly gentle. A nearly imperceptible stretch, a nearly invisible squeeze. The universe had carried that memory across more than 1 billion years, simply to brush past our tiny planet. It is difficult not to find poetry in that. Every gravitational wave is like an ancient letter finally arriving after an impossibly long journey. Its sender no longer exists in the same form. The event itself ended ages before Earth even developed complex life. Still, the message arrives, not written in ink, but written into the geometry of reality itself. This gives astronomers an entirely new way of observing the cosmos. For centuries, nearly everything humanity learned about space came from light. Visible light, infrared light, radio waves, X-rays, gamma rays. All are simply different forms of electromagnetic radiation. But light has limitations. Dense clouds of gas can hide newborn stars. Black holes emit almost no light directly. The earliest moments after the Big Bang remain largely hidden because the young universe was once opaque. Gravity, however, is much harder to stop. Gravitational waves pass through regions that light cannot escape. They carry information from places previously beyond our reach. Some scientists compare this to the difference between watching a silent movie and finally hearing its soundtrack. The universe has always been speaking. Only now are we beginning to listen. And perhaps its oldest memories have not yet reached us. Because gravity travels at the speed of light, every new wave arriving today began its journey somewhere in the distant past. Some may have started before Earth formed, some before our sun was born. Some could even originate from events that occurred shortly after the universe itself came into existence. Every day, entirely unknown chapters of cosmic history continue arriving, unnoticed, invisible, silent, patient. It is a beautiful reminder that time does not erase everything. Sometimes it simply delays the delivery. Even more fascinating is the possibility that space-time itself possesses a kind of resilience. When two black holes merge, space is violently shaken. Yet afterward, the distortions gradually settle into calm once more, like the surface of a pond becoming smooth after a storm. The universe does not remain broken. It heals. The scars become waves. The waves become history, and history keeps moving. There is something deeply familiar in that process. Human lives are also filled with moments that reshape us. Some arrive suddenly, others unfold slowly over years. We cannot always see their influence immediately, but invisible changes continue spreading through our memories, relationships, and choices, long after the original event has passed. In this quiet sense, perhaps people generate their own gravitational memories. Not physical distortions of space-time, of course, but emotional ripples. A kind word spoken decades ago may continue shaping someone else's life. A teacher's encouragement can echo across generations. A parent's patience may influence grandchildren never yet born. Most of these effects are impossible to measure, yet they continue moving outward nonetheless. The universe reminds us that not every important force is visible. Gravity itself cannot be seen, only its influence. Perhaps memory works much the same way. Astronomers are now building even more sensitive gravitational wave observatories. future detectors may operate in space itself, free from Earth's constant vibrations. Projects like the Laser Interferometer Space Antenna, or LISA, hope to detect slower, deeper gravitational waves produced by supermassive black holes millions of times heavier than our Sun. Others aim to listen for signals from the earliest fractions of a second after the Big Bang. If successful, humanity may one day hear echoes from the birth of time itself. Imagine listening to the universe as one might listen to an old forest. At first, there seems to be silence. Then gradually, subtle sounds emerge. Leaves shifting, branches creaking, distant water flowing, tiny insects moving through the undergrowth. The silence was never empty. Our ears simply needed to become more patient. Perhaps the cosmos has always been like this, not silent, only waiting. Waiting for curious minds capable of hearing its oldest stories. Even black holes, once considered the ultimate symbols of disappearance, become storytellers through gravity. Although no light escapes them, their mergers produce unmistakable gravitational signatures. They reveal their masses, their spins, their distance, even their cosmic dance before becoming one. It is as though the universe refuses to let even darkness keep every secret. In the deepest night of space, information still finds a way forward. And perhaps that is one of the quietest lessons hidden among the stars. Nothing truly happens in isolation. Every event leaves traces. Every motion creates influence. Every encounter changes something. Sometimes those changes are obvious. Sometimes they remain almost unimaginably small. Yet they continue traveling, long after we stop noticing them, long after the original moment has passed. As we lie beneath Earth's familiar sky, surrounded by ordinary sounds and ordinary concerns, ancient gravitational waves may be flowing through us this very second. Ripples born from black holes that no longer exist as they once did. Messages older than humanity, older than civilization, older than memory itself. We never feel them. Our bodies remain unaware. Yet the universe continues passing its stories gently through us, one silent wave at a time. Perhaps that is one of the most peaceful thoughts the cosmos offers. Nothing is ever entirely forgotten. The stars may vanish, galaxies may collide, entire worlds may disappear. But somewhere, carried across unimaginable distances, gravity quietly remembers, and it keeps telling the story forever. 9. The ancient echoes floating through empty space. There is one message that has been traveling longer than any other. It began before stars existed, before galaxies filled the darkness, before planets gathered from clouds of dust, long before there were oceans, mountains, or living creatures capable of wondering where they came from. It has crossed nearly the entire history of the universe without ever stopping. And even now, at this very moment, it is quietly passing through the room around you. You cannot hear it. You cannot see it with your eyes, yet it surrounds us constantly. Astronomers call it the cosmic microwave background. You might think of it as the oldest surviving photograph ever taken. Except no one held a camera. The universe created the image itself. To understand why this ancient light still exists, we must travel back almost 13.8 billion years to a time when the universe was unimaginably different from the one we know today. Immediately after the Big Bang, everything was astonishingly hot. Not simply warm, not even as hot as the center of a star. The temperature was so extreme that ordinary atoms could not exist. Electrons rushed freely through a dense sea of energetic particles. Light itself struggled to travel very far before crashing into another charged particle. Imagine standing inside an impossibly thick fog. No matter how bright your flashlight, the beam cannot travel more than a few steps before scattering. The early universe was like that. It glowed brilliantly, yet nothing could see across it. For hundreds of thousands of years, space remained filled with this glowing fog. Then, slowly, something remarkable happened. As the universe expanded, it cooled. Temperatures gradually fell enough for electrons to combine with atomic nuclei, creating the first stable hydrogen and helium atoms. Suddenly, the endless fog began to disappear. Light no longer bounced endlessly between free electrons. For the first time, photons were free. They streamed outward in every direction. Many of those same photons are still traveling today. They have never stopped. they have never turned around. For nearly the entire lifetime of the universe, they have crossed expanding space without rest. Eventually, a tiny fraction of them reached Earth. Even tinier numbers continue reaching your body every second. In a very real sense, ancient light from the birth of the cosmos is touching you right now. Of course, after nearly 14 billion years of expansion, those photons no longer appear as visible light. Space itself has stretched them. Their wavelengths have become longer and longer, transforming brilliant early radiation into faint microwaves. The message remains, only its voice has grown softer. If your eyes could somehow detect microwave radiation, the entire sky would glow with an incredibly gentle light, not concentrated in one direction, not shining from a single star, but surrounding us equally from every corner of the heavens. It is almost perfectly uniform. Almost. That tiny word carries enormous significance. Because although the cosmic microwave background appears remarkably smooth, careful measurements reveal incredibly small temperature differences, only a few millionths of a degree. At first glance, they seem almost meaningless. Little patches slightly warmer, little patches slightly cooler. Yet those microscopic variations became everything. The slightly denser regions contained just a little more matter than their surroundings. Gravity slowly strengthened those tiny differences over millions of years. Clouds grew, galaxies formed, stars ignited, planets emerged. Eventually, somewhere inside one unremarkable spiral galaxy, life looked upward and began asking questions. Every mountain, every tree, every human being, every thought ever imagined can trace its origins back to those faint irregularities frozen into the oldest light in existence. Without them, the universe might have remained nearly featureless forever. A smooth ocean of particles, no galaxies, no stars, no Earth, no one. It is astonishing that something so unimaginably small could shape everything that followed. Perhaps the universe itself reminds us that great stories often begin with almost invisible beginnings. Scientists first discovered this ancient glow almost by accident. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were attempting to eliminate mysterious background noise from a sensitive antenna. No matter where they pointed it, the faint signal remained. They checked their instruments. They examined electrical interference. They even cleaned out pigeons nesting inside the antenna, wondering whether the birds had somehow contaminated their measurements. Still, the mysterious signal refused to disappear. Eventually, they realized they were not detecting equipment noise at all. They were listening to the oldest light in the universe. Imagine spending your day trying to remove static from a radio, only to discover that the static is actually the whisper of creation itself. Sometimes the greatest discoveries arrive quietly, not with explosions, not with dramatic announcements, simply with patient curiosity. Since then, increasingly sophisticated spacecraft have mapped this ancient radiation in extraordinary detail. Satellites such as COBE, WMAP, and Planck transformed the faint microwave glow into detailed images showing the earliest structure of the young universe. Although these colorful maps often appear artistic, the colors represent minute temperature differences invisible to human senses. They reveal a universe only about 380,000 years old. Compared to its present age, that is almost infancy. If the entire history of the cosmos were compressed into a single human lifetime of 80 years, the cosmic microwave background would capture the universe when it was less than a single day old. Looking at it is not merely looking far away, it is looking back toward the beginning of everything familiar. And still, the message continues arriving. Every second, every minute, every year. Unlike letters that fade with age, this one grows no older than the speed of light allows. It simply keeps traveling, patiently, silently, across expanding space. There is something deeply comforting about that persistence. Human civilizations rise and fall, languages appear and disappear, books decay, memories fade. Even mountains slowly wear away beneath wind and rain. Yet the universe continues carrying its oldest story with extraordinary care, as though time itself has become the messenger. Perhaps this also changes the way we think about emptiness. When we picture deep space, we often imagine perfect silence, perfect darkness, perfect nothingness. But true emptiness scarcely exists. Even the vast spaces between galaxies remain filled with ancient photons crossing unimaginable distances. The vacuum is alive with history. Invisible rivers of light flow endlessly through what seems completely empty. The cosmos never entirely forgets. It simply spreads its memories so thinly that only careful observers notice them. There is another quiet beauty hidden within this realization. Every night, when you look toward the stars, you are not only seeing distant suns, you are also looking through the ancient afterglow surrounding them all. It forms a nearly perfect backdrop behind every galaxy ever photographed, behind every nebula, behind every black hole, a gentle ocean of light, older than them all. It is easy to think of history as something buried beneath the ground, fossils hidden inside stone, ruins beneath forests, ancient bones preserved beneath deserts. The universe stores history differently. It writes its earliest chapters into light itself, then allows those pages to drift forever across space, waiting for curious minds to read them. Perhaps that is why astronomy feels so different from any other science. A geologist uncovers the distant past by digging downward. An archaeologist brushes dust away from forgotten cities. But an astronomer uncovers ancient history simply by looking upward. The farther we see, the farther back we travel. Distance becomes time. Light becomes memory. The sky becomes an archive without end. And perhaps that is the quiet miracle hidden above us every clear night. The oldest message in existence has never stopped speaking. It asks for no attention. It makes no sound. It shines too softly for our eyes to notice. Yet it continues its endless journey through empty space, carrying the memory of a universe just awakening. Every second it crosses another world. Every moment it passes another traveler among the stars. And now, after nearly the entire age of the cosmos, its ancient echo has reached you. Not as a voice, not as a sentence, but as a silent reminder that the universe has been telling its story since the beginning of time. All we have ever needed to do is learn how to listen. 10. Could space remember everything? Some physicists wonder whether information can ever truly disappear, even after everything else is gone. It is a surprisingly simple question. When something vanishes, is it truly lost? Or does the universe continue holding on to its story in ways we have not yet learned to understand? Imagine writing your name across the surface of a calm beach. A gentle wave arrives. The letters dissolve almost instantly. To anyone watching, your message has disappeared. But has it truly ceased to exist? The grains of sand have merely been rearranged. The water has carried tiny traces farther down the shore. The air has shifted slightly as the wave passed. Every change has influenced something else. Nothing has been erased without consequence. The universe often behaves in much the same way. For centuries, scientists assumed that information could simply vanish under the right circumstances. Burn a letter, and the words are gone. Break a glass, and its perfect shape disappears. Watch smoke drift into the sky, and it becomes impossible to reconstruct every swirling motion that created it. Nature seemed comfortable with forgetting. Yet modern physics tells a subtler story. At the smallest scales, the fundamental laws governing particles appear remarkably reluctant to destroy information. Instead, information changes form, it spreads. It becomes extraordinarily difficult to recover. But according to many interpretations of quantum mechanics, it may never be completely erased. This distinction is surprisingly important. Losing access to information is not necessarily the same as destroying it. Imagine shuffling a 1,000-piece puzzle into a gigantic box filled with millions of other puzzle pieces. Finding the original picture would seem impossible, yet every single piece still exists. The image has become hidden rather than eliminated. Perhaps the universe stores information in similarly mysterious ways. This idea becomes especially fascinating when black holes enter the story. For many years, black holes appeared to present a profound paradox. Anything crossing the event horizon seemed destined to disappear forever. Stars, gas, dust, entire planets. Even light itself could never escape once it ventured too close. If information truly vanished inside black holes, one of the deepest principles of quantum physics might be broken. The puzzle became known as the black hole information paradox. It has occupied some of the greatest scientific minds for decades. Among them was Stephen Hawking. In the 1970s, Hawking made another astonishing discovery. Black holes are not completely black. Thanks to quantum effects occurring near the event horizon, they slowly emit an incredibly faint form of radiation. Today we call it Hawking radiation. Over unimaginably long periods, this radiation would cause black holes to lose mass. Eventually, given enough time, far longer than the current age of the universe, a black hole could evaporate entirely. And that raised an unsettling question. If the black hole eventually disappears, what happens to everything that once fell inside? Does the information vanish with it, or has it somehow been preserved all along? For decades, physicists debated this mystery with extraordinary intensity. Different ideas emerged. Some suggested information might escape in subtle patterns hidden within Hawking radiation. Others proposed that it remains encoded on the event horizon itself. Still others explored entirely new ways of understanding space-time. No single explanation has yet achieved universal acceptance. Yet one remarkable lesson has already emerged. Nature appears deeply resistant to true forgetting. The more scientists investigate, the more they suspect that information survives in forms far stranger than anyone first imagined. This leads to another beautiful possibility. Perhaps space itself is not merely an empty stage where events unfold. Perhaps it quietly participates in the story. Imagine fresh snow covering an untouched field. A traveler walks across it. Hours later, the traveler has disappeared beyond the hills. Yet the snow remembers. Footprints remain. Not because the snow possesses consciousness, but because interactions always leave traces. Space may behave in an equally subtle manner. Mass bends it, energy shapes it, motion ripples through it. Every interaction changes the geometry of the universe, however slightly. Some physicists have even explored whether the boundaries of space might preserve astonishing amounts of information. One of the most intriguing ideas inspired by this possibility is known as the holographic principle. The name sounds almost like science fiction, yet the concept arises from serious attempts to understand black holes and quantum gravity. Very roughly speaking, it suggests that the information describing a three-dimensional region of space might somehow be encoded upon a two-dimensional boundary, rather like a hologram appearing three-dimensional despite being stored on a flat surface. This does not mean our universe has been proven to be a hologram. It has not. Rather, it is one mathematical framework that has proven surprisingly useful in certain areas of theoretical physics. Whether it ultimately describes our own universe remains an open question. Still, the idea invites quiet reflection. Perhaps reality is richer than ordinary intuition allows. Perhaps dimensions themselves hold secrets we have only begun to glimpse. Meanwhile, quantum physics introduces another curious feature. Particles that interact can become connected through quantum entanglement. Even after separating across enormous distances, measurements performed on one particle remain correlated with measurements on the other in ways that classical physics cannot fully explain. These connections do not allow messages to travel faster than light, yet they remind us that relationships established in the past can continue shaping the future. The universe is full of hidden connections. Perhaps memory itself is not always localized. Perhaps it can be woven into relationships rather than objects. That thought echoes beyond physics. Human memory rarely exists in only one place. A childhood home preserves part of a family's history. Old photographs preserve another part. Songs awaken emotions long forgotten. A familiar scent suddenly restores moments buried beneath decades. No single object contains an entire life. Yet together, countless small traces recreate something astonishingly complete. Maybe the universe also remembers through countless scattered fragments. No single photon, no single atom, no single gravitational wave. But together, an unimaginably vast tapestry of interactions, preserving the story of everything that has ever happened. Even if no observer could ever reconstruct it, there is something quietly comforting in that possibility. It suggests that existence leaves echoes beyond immediate experience. Every star that shines changes the surrounding universe. Every supernova enriches future worlds with heavier elements. Every collision reshapes galaxies. Every passing moment becomes part of an ever-growing cosmic history. Perhaps nothing meaningful simply evaporates into absolute nothingness. Instead, events become woven into the fabric of reality itself, sometimes visibly, sometimes invisibly, always influencing what comes next. Of course, science remains careful. Many of these questions remain unanswered. Physicists continue searching for a successful theory uniting quantum mechanics with general relativity. Experiments continue, new mathematical ideas appear, old assumptions are challenged. The universe has surprised humanity many times before. There is every reason to believe it still holds deeper mysteries waiting beyond the horizon of our understanding. Perhaps that uncertainty is part of its beauty. Not every question needs an immediate answer. Some questions exist to keep curiosity alive, to remind us that knowledge is not a destination, but a journey stretching farther than any individual lifetime. As the night sky slowly turns above us, stars quietly emit their light into the darkness. Gravity continues sculpting invisible paths. Ancient photons continue crossing intergalactic space. The faint afterglow of creation still surrounds every corner of the heavens, and somewhere hidden within these vast patterns, the universe may be preserving far more than we can presently imagine. Perhaps space remembers, not in the way people remember, not with thoughts, not with feelings, but through the unbroken continuity of physical law. Through every ripple, every field, every quantum interaction, every subtle transformation connecting one moment to the next. If that is true, then the cosmos is not merely expanding through time. It is quietly carrying the complete history of itself forward, moment by moment, without ever needing to write a single word. The oldest stars may one day fade. Galaxies may drift beyond one another's reach. Even black holes may eventually evaporate into darkness. Yet if information truly cannot disappear, then the universe may never become completely empty. Somewhere, in forms too subtle for us to recognize today, every sunrise, every heartbeat, every distant supernova, and every whisper of ancient light may still remain, woven forever into the endless fabric of space itself. And perhaps that is the gentlest possibility of all, that nothing which has ever truly existed is entirely forgotten. The universe simply remembers in a language we are only beginning to learn. 11. The day every clock stops agreeing. Imagine carrying the finest clock ever built to the farthest reaches of the universe. Its gears never fail. Its atoms remain perfectly stable. Every vibration is measured with astonishing precision. On Earth, it would lose less than a second over billions of years. Yet one day, even that remarkable clock may no longer be able to tell you what time it is. Not because it has broken, but because the universe itself may stop providing a meaningful way to measure time at all. Tonight, let us drift into one of the quietest and most fascinating possibilities modern physics has ever imagined. A future where every clock in existence slowly stops agreeing with every other, until the very idea of before and after begins to lose its familiar meaning. For most of human history, time has felt wonderfully dependable. Morning follows night, the seasons return, hearts beat, stars rise and set. Even when we discovered that time flows differently depending on speed and gravity, those differences remained small enough that everyday life still felt comfortably ordered. Einstein showed us that time is not universal. A clock aboard a fast-moving spacecraft ticks more slowly than one resting peacefully on Earth. A clock placed near a massive black hole runs differently from another floating far away in empty space. Today, these effects are no longer merely theoretical. The satellites that allow GPS navigation to work must constantly correct for tiny differences caused by both their speed and Earth's gravity. Without those adjustments, navigation systems would drift by kilometers in only a single day. Already, every clock in our universe experiences time just a little differently. Yet these differences are manageable because they exist within a universe filled with reference points. Planets orbit stars, stars circle galaxies, galaxies move through clusters. Everywhere we look, motion provides patterns against which time can be compared. But the distant future may slowly erase those familiar patterns. The universe has been expanding ever since the Big Bang. Even more surprising, that expansion is accelerating. Galaxies are gradually moving farther apart, carried not through space like ordinary motion, but because space itself continues stretching. This expansion unfolds so gently that we barely notice it on local scales. Gravity keeps our solar system together. It holds galaxies intact. It binds galaxy clusters across millions of light years. But over unimaginable spans of time, the accelerating expansion will increasingly dominate the largest structures of the cosmos. One by one, distant galaxies will slip beyond what astronomers call the cosmic horizon. Not because they exceed the speed of light through space, but because the expanding fabric of space carries them away faster than their light can ever reach us again. Future civilizations, if any still exist, may eventually see only their own isolated galaxy. Everything else will simply fade from view. Without those distant galaxies, many of our methods for measuring cosmic time would disappear. Today, astronomers estimate the universe's expansion by observing galaxies across billions of light years. Those observations allow us to reconstruct cosmic history. But when nearly every external reference vanishes, such measurements become impossible. The universe itself begins to lose its visible clock. Even inside galaxies, time continues to reshape reality. Stars are constantly burning their nuclear fuel. Our sun has enough hydrogen to shine for about another 5 billion years. Larger stars burn even faster. Smaller red dwarfs survive much longer, some for trillions of years. Eventually, however, even the longest-lived stars exhaust their fuel. The bright night sky slowly grows darker. The familiar rhythm of stellar birth and death begins to slow. Without fresh clouds of gas, new stars become increasingly rare. Galaxies that once sparkled with billions of brilliant suns gradually settle into populations of cooling white dwarfs, quiet neutron stars, and silent black holes. The cosmic calendar becomes increasingly difficult to read. The clocks built into the lives of stars begin disappearing one after another. Yet perhaps the strangest challenge comes from the nature of entropy. Entropy is often described as the tendency toward increasing disorder, but another way to understand it is as the reason time appears to move in one direction. We remember yesterday, not tomorrow. Ice cubes melt instead of spontaneously reforming. Smoke spreads through a room rather than gathering neatly back into a candle. These familiar experiences all reflect entropy steadily increasing. As long as entropy changes, physical processes continue unfolding. Events happen. Differences emerge. History accumulates. But imagine a universe that has expanded for unimaginable lengths of time. Matter grows sparse. Temperatures approach nearly uniform values. Energy differences become increasingly difficult to find. Without useful energy gradients, fewer physical changes occur. Everything becomes quieter, more uniform, less dynamic. In such a universe, defining the passage of time becomes surprisingly difficult. After all, how do we notice time passing? Usually because something changes. A candle burns lower, leaves fall, mountains erode, children become adults, galaxies collide. But if almost nothing changes anymore, what marks the passage of one moment from the next? Some physicists suggest that time itself may be deeply connected to change. Without meaningful change, time remains as a mathematical parameter within physical equations, yet its lived significance begins to dissolve. A universe without events may still possess time, but it becomes increasingly difficult to experience or even define. Meanwhile, gravity introduces its own complexities. Black holes, the densest objects known, dramatically warp space-time. Near their event horizons, time slows relative to distant observers. A traveler falling toward a black hole experiences only minutes or hours, while someone watching from afar could witness millions or even billions of years passing. Neither observer is wrong. Both simply follow different paths through space-time. Now imagine an ancient future where only scattered black holes remain among vast, empty distances. Every surviving observer, wherever they might exist, experiences time differently, depending upon their surroundings. There is no longer a single shared cosmic rhythm. Every remaining clock follows its own story. Eventually, even black holes themselves are expected to slowly evaporate through Hawking radiation. This astonishing prediction suggests that black holes are not perfectly eternal. Over periods vastly exceeding the current age of the universe, they gradually lose mass by emitting extraordinarily faint radiation. The larger the black hole, the longer this process takes. A supermassive black hole may require around 10 to the power of 100 years, or even longer, to completely disappear. Those numbers are so enormous that ordinary language struggles to contain them. They are durations beyond civilizations, beyond stars, beyond galaxies. They belong to a future almost impossible to picture. When those final black holes fade, the universe may enter an era of astonishing stillness. Tiny particles drift through enormous emptiness. Radiation stretches into wavelengths larger than galaxies once were. Events become unimaginably rare. In such an environment, what could any clock possibly measure? A second compared to what? A year marked by which orbit? A century defined by which cycle? Many of the repeating patterns that give time its practical meaning would no longer exist. Some speculative theories suggest that quantum fluctuations may continue indefinitely. Others imagine that entirely new physical processes could emerge over such immense timescales. Still others propose that the universe itself may someday undergo transformations we do not yet understand. Science remains wonderfully honest about these possibilities. Much of the far future lies beyond what current observations can fully confirm. Yet even our best supported models reveal a remarkable truth. Time is not simply a backdrop upon which reality unfolds. It is woven together with matter, energy, gravity, motion, and change. Remove enough of those ingredients, and our familiar experience of time begins quietly unraveling. Perhaps that is one of the most beautiful lessons the universe offers. The ticking of a clock is never just the movement of hands across a dial. It is a conversation between countless physical processes unfolding together. The beating of hearts, the burning of stars, the spinning of galaxies, the expansion of space itself. Each participates in the grand symphony that allows us to say this moment follows the last. And maybe in the unimaginably distant future, when every clock finally tells a different story, the universe will not have lost time. It will simply have entered a chapter where time no longer resembles the companion we have always known. For now, though, our clocks still agree well enough. The stars continue shining, the galaxies still fill the night beyond our sight, and each quiet second that passes carries us gently forward through one of the greatest mysteries ever discovered, the extraordinary, beautiful flow of time itself. 12. The universe. After every last fire has faded. There may come a time so unimaginably distant that every familiar source of light has disappeared. No stars burning quietly in the darkness. No glowing nebulae giving birth to new suns. No galaxies shining across impossible distances. Only an endless, silent night stretching farther than any mind could truly picture. Today, the universe still feels alive. Every second, somewhere among the trillions of galaxies, stars ignite, planets form, and black holes collide. Light races across space, carrying stories from worlds that may no longer exist. The cosmos appears dynamic, constantly changing, constantly creating. But nothing burns forever. Every star is spending a limited supply of nuclear fuel. Some are generous, living for hundreds of billions or even trillions of years. Others exhaust themselves in only a few million years. The difference is enormous on human timescales. On cosmic timescales, both are brief. Eventually, star formation itself begins to slow. Galaxies slowly consume or lose the vast clouds of hydrogen needed to create new stars. Some gas becomes locked inside dim stellar remnants. Some is blown into intergalactic space by ancient explosions. Some falls forever towards supermassive black holes. Little by little, the universe uses up the ingredients that once made it bright. Astronomers sometimes call this era the end of the stelliferous age, the age of stars. It is difficult to imagine because every story humanity has ever lived has taken place during this brief, luminous chapter. We have never known a universe without starlight. To us, stars seem permanent. To the universe, they are only a passing phase. After enough time, the final generation of stars slowly fades away. The largest collapse dramatically, the smallest quietly cool. White dwarfs radiate away the remaining heat over unimaginable stretches of time. Eventually, they become black dwarfs, objects so cold they emit virtually no visible light. No one has ever seen a black dwarf. the universe itself is still far too young. Not enough time has passed for one to form. Yet according to current understanding, they represent one possible future destination for nearly every ordinary star. Imagine standing in such a universe. There would be no familiar constellations, no Milky Way arching overhead, no distant galaxies decorating the night. The sky itself would appear almost completely empty. Darkness would no longer be something between stars. Darkness would be nearly everything. Even then, gravity would continue its patient work. Ancient stellar remnants would orbit quietly through space. Some would occasionally drift close enough to merge. Others would wander for trillions upon trillions of years without ever encountering another object again. Motion would continue, but spectacle would become extraordinarily rare. If someone could somehow survive into this distant era, warmth would become the rarest treasure imaginable. Almost every natural heat source would be gone. The average temperature of the universe would continue inching closer toward absolute zero, not reaching it, but approaching it forever. Every remaining object would slowly surrender its stored energy to space. Heat would spread thinner and thinner until meaningful temperature differences almost disappear. The universe would not freeze in a sudden catastrophe. It would cool gradually, almost imperceptibly, over spans of time so immense that even words like slow lose their meaning. This possible future is often connected to an idea known as heat death. Despite the dramatic name, it is not an explosion, not a collapse, not a final battle between opposing forces. Instead, it is equilibrium, everything becoming nearly the same temperature. Energy remaining present, but so evenly distributed that no useful work can be extracted from it. No engines, no metabolism, no weather, no burning stars. Complex processes require differences. Hot beside cold, dense beside empty, high energy beside low. As those differences disappear, change itself becomes increasingly difficult. The universe does not stop existing. It simply becomes quieter than anything we have ever experienced. Curiously, quantum physics still refuses to allow perfect stillness. Even empty space possesses tiny fluctuations. Virtual particles briefly appear and vanish. Fields continue fluctuating at microscopic scales. Silence, even here, is never perfectly silent. Reality seems unwilling to become completely motionless. Some theories even suggest astonishingly rare events may continue occurring. Given enough unimaginable time, random fluctuations might assemble unexpected structures. Perhaps isolated particles momentarily organize into complex arrangements before dissolving again. The probabilities are extraordinarily tiny, yet when time becomes effectively limitless, even impossibly unlikely events begin to deserve consideration. This is one reason the far future of cosmology remains such a fascinating field. Our equations reach extraordinary distances into time, but they also remind us how much remains uncertain. Will protons eventually decay? Will black holes completely evaporate? Does dark energy remain constant forever? Or does some deeper physics still wait to be discovered? Each answer changes the ending slightly. Yet every version shares one remarkable idea. The bright universe we know today is temporary. Sometimes that thought sounds unsettling, yet perhaps it can also make the present feel astonishingly precious. Every sunrise on Earth, every glowing nebula photographed by telescopes, every shimmering galaxy visible through long exposures, every warm afternoon beneath our nearest star. These are experiences taking place during one extraordinarily special chapter in cosmic history. We were born not at the beginning, not at the end, but during an age when the universe is still illuminated, when stars still write new stories, when planets still orbit warm suns, when curiosity itself can look outward and ask questions. Perhaps that is one of the greatest coincidences of all. The universe became conscious of itself while light still filled the sky. And maybe that is enough. Because although every fire may eventually fade, the fact that any of them burned at all remains extraordinary. The atoms inside our bodies were forged inside ancient stars. the calcium in our bones, the oxygen we breathe, the iron flowing through our blood. Each began its journey in stellar furnaces that lived and died billions of years before Earth existed. In a very real sense, every heartbeat carries the memory of forgotten suns. Perhaps that is the quiet lesson hidden inside the universe's distant future. Nothing luminous lasts forever. Not stars, not galaxies, not even the brightest eras of cosmic history. Yet their influence continues long after their light has faded. The universe changes. It cools, it expands, it grows quieter. But every chapter leaves traces that shape the next. And somewhere during this fleeting age of warmth and light, we happened to awaken just long enough to notice. Maybe that is the rarest event the cosmos has ever produced. Not merely stars, not merely galaxies, but observers capable of wondering what comes after the final sunset. And perhaps in asking that question, we become one small part of the universe remembering itself. If you've enjoyed drifting through these quiet journeys across space and time, we'd love for you to join us again. There are still countless mysteries waiting beyond the stars, and every new voyage begins with a single moment of curiosity. Until next time, thank you for exploring the universe with us. 13. The last patterns in a quiet universe. By the time the universe reaches this unimaginably distant future, almost everything we recognize today will have disappeared. The bright galaxies that once painted the night sky have long since faded. Stars have exhausted their fuel. Black holes have slowly evaporated into faint whispers of radiation. Even the familiar atoms that make up planets, oceans, and ourselves may no longer exist in the forms we know. At first glance, it seems that nothing remains except an endless darkness stretching beyond imagination. Yet some physicists believe the story may not end with complete chaos. Perhaps, even in the quietest universe imaginable, tiny patterns continue to survive. Not grand structures, not galaxies, not stars. Only the faintest arrangements, small pockets, where order briefly resists the overwhelming pull toward randomness. To understand why this possibility fascinates scientists, we need to think about what order really means. When you pour cream into coffee, beautiful swirling shapes appear for a few moments before blending into a single, uniform color. The swirling patterns disappear. The coffee reaches equilibrium. Nature prefers this direction because disorder, what physicists call entropy, tends to increase. The universe itself behaves in much the same way. Since the Big Bang, matter has naturally moved from simple beginnings toward increasingly complex structures. Gravity gathered hydrogen into stars. Stars forged heavier elements. Those elements formed planets. On at least one small world, chemistry eventually became biology. Complexity blossomed. Yet this flowering of structure was never permanent. Every star that ignites also begins counting down toward extinction. Every organized system slowly disperses energy. Every living organism eventually returns its atoms to the cosmos. Entropy always keeps moving forward. Eventually, after unimaginable trillions upon trillions of years, the universe may approach what physicists call maximum entropy, a state where usable energy has been spread so evenly that almost no meaningful work can occur. Imagine a room where every molecule of air has become perfectly mixed. Nothing dramatic happens anymore. Nothing naturally changes. Everything simply remains. This is sometimes called the heat death of the universe. The name sounds violent. In reality, it is remarkably peaceful. No explosions, no collapse. Only endless stillness. But even perfect stillness may never be perfectly perfect. Quantum mechanics refuses to allow complete silence. Even empty space is not truly empty. Tiny quantum fluctuations constantly appear and disappear. Virtual particles flicker into existence for incredibly brief moments before vanishing again. Today, these fluctuations are almost impossible to notice because the universe is filled with stars, galaxies, radiation, and matter. In the far future, however, these microscopic events could become some of the only activity left. Imagine standing inside an enormous cathedral after everyone has left. The loud conversations are gone. The music has ended. Only the faint creaks of ancient wood and the soft movement of air remain. The quieter the room becomes, the more noticeable the smallest sounds are. Perhaps the future universe behaves similarly. As every larger structure disappears, only the tiniest fluctuations continue whispering beneath the silence. Some researchers have wondered whether these fluctuations could occasionally produce surprisingly organized arrangements. Not because nature is trying to create order, simply because probability allows even extremely unlikely events if given enough time. Imagine shuffling a deck of cards forever. Almost every shuffle looks random. But eventually, perhaps after an incomprehensibly long sequence, you would accidentally recreate the exact original order, not through intention, through chance alone. The same principle may apply across the cosmos. Over timescales so vast they almost lose meaning, random fluctuations might briefly assemble tiny islands of order. A few particles aligned just so. A fleeting configuration carrying slightly less entropy than its surroundings. A temporary pattern emerging from an ocean of randomness before dissolving once again. These patterns would not last. They would not grow into civilizations. Most would disappear almost immediately. Yet their existence reminds us of something remarkable. Randomness does not forbid structure. It merely makes structure exceedingly rare. In today's universe, gravity performs much of the organizing work. It gathers matter, forms stars, builds galaxies, shapes planets. In the distant future, gravity's influence becomes weaker as matter spreads farther apart. Without gravity constantly sculpting the cosmos, any remaining order would arise only through statistical chance. Some physicists even speculate about extraordinarily rare events known as Boltzmann fluctuations. Named after the Austrian physicist Ludwig Boltzmann, these hypothetical fluctuations describe the spontaneous appearance of ordered systems within a universe otherwise dominated by disorder. Most fluctuations would be tiny, perhaps only a handful of particles arranged differently. Larger fluctuations become exponentially less likely. Entire stars forming spontaneously would be fantastically improbable. Galaxies, essentially impossible. Yet mathematics does not always distinguish between impossible and inconceivably unlikely. Given infinite time, even astonishing events become difficult to dismiss completely. This idea has inspired one of cosmology's strangest thought experiments, the Boltzmann brain. Imagine a conscious observer appearing briefly through random fluctuations before disappearing moments later. The concept sounds like science fiction. Many physicists actually regard it as a paradox rather than a prediction. If random observers become statistically more common than observers created through billions of years of cosmic evolution, our understanding of cosmology faces uncomfortable questions. Fortunately, many modern theories avoid this conclusion. Still, the discussion reveals something profound about the relationship between probability and existence. Sometimes the most fascinating scientific ideas emerge not because we believe they happen, but because asking the question forces us to understand reality more deeply. Beyond these speculative possibilities lies another, quieter truth. Patterns do not always require permanence to matter. Think about footprints in fresh snow. They disappear after the next snowfall. Ripples across a pond vanish within minutes. Clouds constantly reshape themselves in the wind. Yet during their brief existence, each pattern is perfectly real. Perhaps the future universe becomes a place where reality itself consists almost entirely of fleeting arrangements. Nothing enduring, nothing monumental, only delicate structures appearing and fading like thoughts passing through an endless mind. There's something strangely comforting about this image. We often imagine permanence as the ultimate goal. We want mountains to stand forever, civilizations to endure, memories to remain untouched. But nature rarely works that way. Instead, beauty often exists precisely because it is temporary. Cherry blossoms fall, sunsets fade, stars burn out. Their endings do not erase their significance. Perhaps the universe itself follows the same philosophy. Its greatest achievements, the galaxies, the planets, the emergence of life, may occupy only a tiny fraction of cosmic history. Yet that brief era contains extraordinary richness. If tiny patterns become the final surviving echoes of order, they serve as gentle reminders of everything that came before. Not memories in the human sense, not conscious recollections, simply the continued possibility that order can briefly emerge, even within overwhelming silence. Perhaps this is one of the deepest lessons modern cosmology offers. The universe is not simply a story moving from order to chaos. It is a continual dance between the two. Order arises, entropy grows, new patterns emerge, old ones dissolve. Nothing remains unchanged, and yet the possibility of structure never disappears entirely. Even near the end of everything, the cosmos may still be quietly experimenting with arrangements of matter and energy, creating delicate patterns too subtle for any observer to witness. No applause, no audience. Only the mathematics of probability unfolding across eternity. In that silent future, there may be no one left to notice these final patterns, no eyes to see them, no minds to understand them. Yet perhaps existence itself does not require an observer to be meaningful. Perhaps the universe has always been quietly creating beauty simply because its laws allow beauty to emerge. And maybe that has been true from the very beginning. 14. Could reality ever start again? For nearly our entire journey, we have been traveling in one direction, forward. From the brilliant birth of the cosmos, through the lives of stars, past the fading of galaxies, across the evaporation of black holes, into an era where even the smallest patterns become rare visitors inside an almost perfectly quiet universe. It feels like the end of a story, and perhaps it is. But there is something curious about endings in physics. They often resemble beginnings more than we expect. When we imagine nothing, we usually picture an empty black room. No light, no sound, no motion, no change. Yet modern physics has repeatedly challenged that intuition. Again and again, nature reminds us that emptiness is far stranger than absence. The vacuum of space is not simply a blank canvas. It possesses energy. It fluctuates. It follows mathematical laws. Even when every visible object has disappeared, the fabric beneath reality may still remain astonishingly active in ways far too subtle for everyday experience. This raises one of the deepest questions cosmologists can ask. Could a universe that has grown unimaginably old somehow give birth to another? Not through magic, not through intervention, simply because the laws of physics permit new beginnings. No one knows the answer, but over the past century, scientists have imagined several remarkable possibilities. One idea begins with quantum fluctuations. Earlier, we explored how empty space is never completely silent. Tiny fluctuations constantly appear and vanish, borrowing energy from the vacuum for incredibly brief moments before returning it. Normally, these events are microscopic. They influence particles, fields, radiation. But what if, somewhere across unimaginable stretches of time, an extraordinarily rare fluctuation became much larger, large enough not merely to rearrange a few particles, but to reshape space-time itself? Some theoretical models suggest that under very specific conditions, a tiny region of space could transition into a new vacuum state, a different configuration of the underlying fields governing the universe. If that happened, something extraordinary might follow. That tiny bubble would not expand inside our universe the way an ordinary explosion does. Instead, it could become its own expanding universe. From the inside, any observers living there would experience something astonishingly familiar. Space would rapidly expand, energy would flood into existence, particles would form, stars would eventually ignite, galaxies would emerge. To them, it would simply look like a Big Bang, not the continuation of an ancient universe. The beginning of everything. The parent universe, meanwhile, might continue quietly existing outside this newborn cosmos, never noticing what had happened. This idea feels almost impossible to picture because our everyday intuition insists that every beginning must happen somewhere inside an already existing space. Modern cosmology gently suggests something stranger. Perhaps new space itself can emerge. Perhaps beginnings do not require an empty stage. Perhaps they create the stage as they unfold. Another possibility comes from an idea known as the cyclic universe. Imagine breathing, inhale, exhale, again and again. Some physicists have wondered whether the cosmos itself could follow a similar rhythm. Instead of expanding forever, perhaps expansion is only one phase of an endless cycle. After incomprehensibly long ages, something causes contraction. The universe slowly collapses. Matter becomes denser. Temperatures rise. Eventually, another Big Bang-like event occurs, beginning a fresh cosmic chapter. Different versions of this idea exist. Some involve extra dimensions. Others rely upon modifications to Einstein's theory of gravity. Still others imagine collisions between vast cosmic membranes existing in higher dimensional space. At present, observations suggest that our own universe's expansion is accelerating because of dark energy. If that acceleration continues forever, a future collapse appears unlikely. Yet scientists continue exploring alternatives because our understanding of dark energy remains remarkably incomplete. The universe has surprised us before. It may do so again. There is also a more subtle possibility. Perhaps our universe is only one region within a much larger reality. Imagine countless bubbles forming inside an endlessly expanding cosmic ocean. Each bubble becomes its own universe. Each develops its own stars, its own galaxies, perhaps even its own laws of physics. This picture is sometimes called the multiverse. In this view, universes are not singular events. They are natural outcomes of an even larger process. Some begin, others grow old. Still others remain forever beyond our ability to observe. Whether this picture describes reality remains unknown. It may even be impossible to test directly. Yet it demonstrates how modern physics has stretched our imagination far beyond the boundaries our ancestors could have conceived. The question itself has changed. Instead of asking, how did the universe begin? Some physicists now ask, how often do universes begin? There is another possibility, one both beautiful and unsettling. Perhaps reality never truly starts again. Perhaps this universe really is unique. Its story unfolds only once. Its stars ignite only once. Its civilizations appear only once. When the final chapter closes, silence remains forever. At first, this sounds melancholy, but uniqueness has its own kind of beauty. A snowflake exists only briefly. A rainbow disappears within minutes. A human life occupies only a tiny moment in cosmic history. Yet their temporary nature often deepens rather than diminishes their meaning. If our universe has only one story to tell, then every galaxy that ever shimmered, every planet that ever formed, every living creature that ever opened curious eyes toward the night sky, becomes part of an unrepeatable masterpiece. Perhaps rarity itself gives existence its value. Interestingly, even the mathematics of entropy hints that complete stillness may be more difficult to achieve than we imagine. Perfect equilibrium is an idealization. Reality often dances around ideals without ever settling precisely upon them. Small fluctuations remain. Quantum uncertainty persists. The laws continue operating. Even in unimaginable emptiness, physics refuses to become completely motionless. It is almost as though nature dislikes absolute endings, not because it seeks purpose, but because its own rules leave room for possibility. That possibility may never produce another universe. Or it may produce infinitely many. We simply do not know. And perhaps that uncertainty is one of science's greatest strengths. Rather than pretending certainty where none exists, cosmology teaches us humility. Each generation uncovers new pieces of the puzzle. Questions once considered impossible gradually become measurable. Ideas once dismissed later become accepted. Others fade away. The conversation itself continues evolving. When people hear that scientists do not know how everything ultimately ends, or whether another beginning could someday emerge, they sometimes imagine this uncertainty as failure. In reality, it is the opposite. Unanswered questions are the engines of discovery. Every telescope pointed toward the sky, every equation written across a chalkboard, every spacecraft launched beyond Earth exists because someone admitted, we don't yet understand. There is something wonderfully human about that. Long before telescopes existed, our ancestors also stared upward, asking where everything came from. Today, our instruments have become unimaginably sophisticated, yet the feeling remains remarkably familiar. Wonder. Perhaps that is the one pattern that has survived every era we have explored. Stars came and went. Galaxies drifted apart. Black holes evaporated. Even matter itself may eventually disappear, yet curiosity accompanies every step. It follows us from the first campfires beneath ancient skies to the edge of the universe's possible future. And maybe that is fitting, because whether reality begins only once or endlessly begins again, the greatest miracle may not simply be that a universe exists. It may be that somewhere within one fleeting chapter of its immense history, tiny collections of atoms learned to ask where they came from. The cosmos became aware of itself, however briefly. Perhaps that awareness is as extraordinary as any Big Bang. Perhaps every question we ask is itself a small beginning, a new universe of understanding unfolding inside the quiet landscape of the human mind. And if the far future ever reaches a silence so complete that another beginning becomes possible, then perhaps the greatest symmetry of all is this: the end would not erase the story. It would simply become the place where another question first begins. 15. Beyond the edge of time. There is a habit the human mind finds almost impossible to escape. Every story has a beginning, a middle, and an ending. Every road stretches from one place to another. Every heartbeat follows the last. Every sunrise promises another tomorrow. We are creatures built from sequences, living inside the quiet rhythm of cause and effect. So naturally, when we imagine the far future of the universe, we ask the same simple question: what happens next? But the deepest theories in modern physics suggest that one day, unimaginably far beyond the final stars, beyond the last black holes, beyond even the slow fading of particles themselves, that question may simply stop making sense. Not because nothing exists, but because next itself may lose all meaning. Tonight, let us drift toward that astonishing possibility, not as a frightening destination, but as one final, quiet meditation on the nature of reality itself. To understand why time could someday lose its meaning, we first have to ask a surprisingly difficult question. What exactly is time? It feels obvious. Seconds pass, clocks tick, the earth rotates, atoms vibrate, our bodies age. Yet none of these things are actually time. They are only processes that happen within time. Imagine removing every moving object from existence. No stars orbit, no planets spin, no atoms vibrate, no light travels, no particles collide. Would time still pass? Physics offers no universally accepted answer. According to Einstein's relativity, time is woven together with space into a single fabric called space-time. Objects move through it. Gravity bends it. Mass stretches it. Yet relativity itself never tells us why time flows only in one direction. The equations are strangely symmetrical. Most of them work equally well whether time runs forward or backward. The mathematics seems almost indifferent, and yet our experience is not. We remember yesterday, we cannot remember tomorrow. A cup falls and shatters. The pieces never leap upward to rebuild themselves. Ice melts into water. Warm coffee cools. Smoke spreads through the air. Everything appears to move in only one direction. Physicists call this the arrow of time. Surprisingly, the arrow is not built directly into the laws of motion. Instead, it seems to emerge from something even deeper: entropy. Entropy is often described as disorder, although a better description might be the number of possible arrangements. A neatly stacked deck of cards has relatively few possible configurations. A shuffled deck has enormously more. Nature almost always evolves toward states with more possible arrangements. That statistical tendency gives us the direction we experience as time. Past has lower entropy. Future has higher entropy. The universe itself appears to have begun in an astonishingly low entropy condition. That single fact may be the reason time has a direction at all. Without it, yesterday and tomorrow might be indistinguishable. Now imagine carrying this process unimaginably far into the future. Stars disappear, galaxies fade, black holes evaporate. Matter becomes sparse. Energy spreads nearly evenly across all of space. Eventually, entropy approaches its maximum possible value. Nothing dramatic happens. There is simply no remaining imbalance to drive meaningful change. No gradients, no flowing heat, no concentrated energy, no organized structures. everything approaches equilibrium. This idea is sometimes called heat death. The name sounds violent. In reality, it describes extraordinary stillness. Not an explosion, not destruction, just the gradual fading of differences. Imagine placing a drop of ink into a glass of water. At first, the drop is concentrated. Over time, it spreads until every part of the water contains nearly the same amount. Once completely mixed, nothing interesting continues to happen. The system has reached equilibrium. The future becomes almost indistinguishable from the present. Scale that simple image to the entire observable universe. Eventually, every remaining source of usable energy becomes exhausted. Without differences, nothing performs work. Without work, few meaningful events occur. And without meaningful events, what exactly measures the passage of time? This question becomes even stranger when we think about clocks. Every clock depends upon change. A pendulum swings, quartz crystals vibrate, atoms transition between energy levels, Earth rotates, pulsars spin. Even the most precise atomic clocks measure repeated physical processes. But what if no repeating process remains? Suppose every particle capable of interaction has already decayed. Suppose every black hole has evaporated. Suppose temperature differences no longer exist. Suppose nothing changes in any measurable way. Could a clock still exist? Perhaps not. Without change, the very concept of measuring time becomes impossible. Some physicists therefore suggest that time is not a fundamental ingredient of reality. Instead, time may emerge from change itself. No change, no meaningful time. This remarkable idea appears in several modern approaches to quantum gravity. Some theories even propose that the deepest equations describing reality contain no explicit time variable at all. Time may arise only when complex systems interact. Our flowing experience could be something like an emergent property, much as temperature emerges from countless microscopic molecular motions. Individual molecules do not possess temperature. Groups of trillions do. Perhaps reality works similarly. Individual quantum states may not contain time. Only enormous collections of interacting particles generate the familiar flow we experience every day. If so, then the disappearance of complex interactions might also mean the disappearance of experienced time. Not because time stops, because there is no longer anything capable of experiencing sequence. This brings us to one of the most beautiful philosophical questions in science. If absolutely nothing changes, can we honestly say that time is passing? Imagine a perfectly frozen universe. Every particle motionless, every field constant, every distance unchanged. Suppose this condition lasted 1 second, or 1 trillion years. How could anyone tell the difference? Without events to compare, duration itself becomes meaningless. The words 1 year lose their definition. Even eternity becomes impossible to distinguish from an instant. This idea echoes something surprisingly familiar. When we sleep deeply without dreams, hours can disappear in what feels like an instant. No memories form, no events mark their passage. Our awareness simply resumes later. Now imagine extending that intuition beyond all imagination. Not unconsciousness, not sleep, simply the absence of change itself. The universe would contain no before and after in any practical sense. Some researchers have explored an even more radical possibility. Perhaps the universe is fundamentally timeless. What we perceive as flowing time may emerge from relationships between physical systems, rather than existing independently. Imagine a vast collection of photographs scattered across a table. Each image captures a different arrangement of reality. None of the photographs actually moves. Yet if an observer examines them in a particular order, a story appears. Motion emerges. History emerges. Time appears. Perhaps reality resembles something like this. The universe could consist of countless possible configurations. Our conscious experience traces one path through them, creating the sensation of flowing time. This remains highly speculative, but it illustrates how profoundly our understanding of time continues to evolve. The deeper we investigate reality, the less solid time appears. Ironically, the thing that feels most immediate in everyday life becomes one of physics' greatest mysteries. Einstein himself once wrote, after the death of a close friend, that for those who believe in physics, The distinction between past, present, and future is only a stubbornly persistent illusion. He did not mean our experiences are unreal. He meant that reality may possess a structure far stranger than our daily intuition suggests. Perhaps every moment somehow exists together within space-time. Perhaps flow belongs more to consciousness than to the universe itself. Or perhaps an even deeper theory still waits beyond our current understanding. No one knows. That uncertainty is not a weakness of science. It is one of its greatest strengths. Every answer opens another question. Every horizon reveals another beyond it. As we drift toward the ultimate future of the cosmos, we gradually discover that the universe does not simply become darker. It becomes quieter, simpler, more uniform. Eventually, perhaps so uniform that asking what happens next becomes like asking what lies north of the North Pole. The question itself no longer points anywhere meaningful. And yet there is something unexpectedly peaceful about that thought. Our lives unfold inside a universe rich with differences. Light and shadow, heat and cold, birth and death, motion and rest. These contrasts allow stories to exist. They allow memory. They allow music. They allow curiosity. They allow us. The very fact that we can wonder about time means we inhabit one of the rare chapters in cosmic history where change still fills the universe with endless possibilities. Perhaps that is the quiet gift hidden within all these immense timescales. Not sadness for the distant future, but gratitude for the extraordinary present. Because here, beneath ordinary skies, surrounded by ticking clocks and moving stars, time still carries us gently forward, one beautiful moment after another. 16. The endless story that may never truly end. We have traveled farther than almost any story dares to go, far beyond the birth of stars, beyond the rise and fall of galaxies, past the slow fading of light itself, beyond the final whispers of black holes, the last fragile patterns drifting through an almost silent universe, and even to the strange possibility that time itself may eventually lose its familiar meaning. Standing here at the edge of everything we can imagine, one question quietly remains. Has the story finally ended? Our instinct says yes. Every story we have ever known eventually reaches its last page. Every song ends with its final note. Every journey arrives somewhere. And yet, the universe has taught us something remarkable throughout this voyage. Again and again, whenever we believed we had reached the end of understanding, another horizon quietly appeared beyond it. Perhaps reality is not a book with a final chapter. Perhaps it is more like an ocean. Every horizon that seems absolute slowly gives way to another, stretching farther than we ever expected. This has happened throughout the history of science. There was a time when people believed Earth stood at the center of everything. Then we discovered the solar system. Later, we learned that our sun was only one ordinary star among hundreds of billions inside a galaxy. Soon after, we realized our galaxy itself was only one among trillions scattered across an expanding universe. Each answer enlarged the mystery, not because science failed, because reality proved richer than imagination. Perhaps the future will continue that tradition. Maybe generations yet unborn, if any civilizations endure long enough, will uncover entirely new layers of existence that we cannot presently conceive. Perhaps today's deepest theories will one day appear as incomplete as ancient maps that ended with the words, "Here be dragons." There is something wonderfully humbling about that thought. For all our telescopes, particle accelerators, mathematical equations, space probes, and supercomputers, humanity has only begun asking questions. We are children standing on the shore of an immense cosmic sea. Every discovery fills another handful of sand into our understanding, yet the ocean stretches endlessly beyond. Sometimes people imagine science as a collection of answers. In truth, it is equally a collection of beautiful questions. Why is there something rather than nothing? Why do the laws of physics have the values they do? Why does mathematics describe reality so astonishingly well? What happened before the earliest moment we can observe? Does the universe exist alone, Or is it part of something vastly larger? Each question leads naturally toward another, like stars appearing one by one as evening falls. Perhaps this endless chain of curiosity reflects something fundamental about existence itself. Maybe reality is not built to be completely understood, not because it hides from us, but because every level of understanding opens the door to deeper patterns waiting beyond. Think of a child looking through a telescope for the very first time. They discover the moon. Later they learn about planets, then galaxies, then black holes, then quantum fields. Each revelation does not replace the previous one. It expands it. Knowledge grows outward like ripples across a still lake. Perhaps the universe itself unfolds similarly, every ending becoming another beginning. This idea appears surprisingly often throughout nature. A forest burns. Years later, new life emerges from enriched soil. A massive star dies in a brilliant supernova. Its scattered elements eventually become planets, oceans, and living beings. Even our own bodies tell this story. Nearly every atom inside us once belonged to ancient stars that vanished billions of years before Earth existed. Endings constantly become beginnings. Transformation quietly replaces permanence. Maybe that pattern extends further than we can presently see. Even if our universe eventually reaches heat death, even if time loses its familiar direction, even if space-time itself dissolves into something beyond current physics, perhaps those events are not absolute conclusions. Perhaps they are transitions whose meaning we have not yet learned to recognize. Science cannot currently confirm such ideas, nor can it rule them out completely. The honest answer remains beautifully simple. We do not know. There is extraordinary freedom inside those three words. We do not know. Far from diminishing wonder, they protect it. They leave room for discovery, room for imagination guided by evidence, room for tomorrow's insights. Perhaps that is why the night sky has never stopped inspiring us. For thousands of years, every civilization has looked upward. The same stars watched over ancient shepherds, ocean navigators, astronomers, poets, children lying on blankets beneath summer skies. The questions changed, the instruments improved, but the feeling remained astonishingly constant: wonder. Curiosity may be one of the universe's rarest creations. Out of countless galaxies, among unimaginable numbers of stars, tiny collections of atoms learned to ask where they came from. The universe became capable of observing itself. Carl Sagan once described us as a way for the cosmos to know itself. Whether taken poetically or scientifically, there is profound beauty in that idea. The hydrogen forged shortly after the Big Bang eventually became brains capable of contemplating the Big Bang. The same laws governing distant galaxies also guide the electrical signals moving quietly through our own thoughts at this very moment. We are not separate from the universe. We are one of its countless expressions. For a brief moment in cosmic history, the universe opened its eyes. Perhaps someday those eyes will close. Perhaps other eyes will open elsewhere. Perhaps they already have. The cosmos may be filled with questions asked in languages we cannot imagine, by beings living beneath unfamiliar constellations. Or perhaps ours is the only voice ever to wonder. Either possibility is equally breathtaking. As our journey slowly comes to rest, there is one final thought worth carrying home. When we first began, the universe seemed impossibly large, almost overwhelming. Billions of galaxies, trillions of stars, time measured not in years, but in billions upon billions of years. Yet somewhere along the way, something quietly changed. The universe no longer felt merely enormous. It began to feel intimate, not because it became smaller, but because we recognized our place within it. Every breath we take contains atoms older than Earth. Every heartbeat echoes physical laws written into reality nearly 14 billion years ago. Every glance toward the stars connects us with light that has traveled across unimaginable distances simply to arrive here, tonight. We have always belonged to this story. We were never outsiders looking in. We are one chapter among countless others. And perhaps that is the deepest comfort cosmology can offer. The universe is vast beyond comprehension, yet somehow, against staggering odds, it produced moments like this. A quiet evening, a curious mind, a journey across space and time undertaken not by a spacecraft, but by imagination. Whether reality stretches infinitely onward, whether new universes bloom beyond ours, whether time itself someday dissolves into mysteries still beyond mathematics, or whether this single cosmos tells its story only once, the wonder remains the same. Because the greatest mystery has never been simply how the universe ends. It has always been that it exists at all. And that, for one fleeting instant inside its immense history, we were here to wonder about it. So tonight, as the stars continue their silent journeys above, perhaps you can rest knowing that you are made from the same ancient story we have been following all along. A story written in gravity, in light, in time, in atoms older than memory. A story with beginnings we are still learning to understand, and endings that may never truly be endings at all. Perhaps somewhere beyond every horizon, another chapter is already waiting, not demanding to be solved, only inviting us to keep wondering. Thank you for spending this peaceful journey through cosmic time with us. If these quiet stories have helped you relax, sparked your curiosity, or simply carried your thoughts a little farther among the stars, we'd be honored to have you join us again on our next voyage. Until then, close your eyes, breathe gently, and remember that above you, the universe is still unfolding, patiently, silently, and beautifully, one mystery at a time. Sleep well, and may the cosmos continue whispering its endless stories through your dreams.